Like this?
We have no wireless one.
Yeah, but I don't. Yeah, I know. I would just prefer this one. It is on. Yeah. Is this better? At least you can hear me here now. Yeah, I know. It works now. And then, with an even further delay, let's start this invited session on hydraulic systems, advanced detection and security. The session is organized by Lisa Torres, Erik de Duvele, and Joachim Blaser. My co-chair is Christine Verde. She's from Mexico, and you probably know her, all of you. She's one of the organizers of the conference, chair of the technical committee. And we have 6 papers today. And let's start with the first one, which will be presented by Vincent Puig from Barcelona, and it's entitled Nodal Hydraulic Head Estimation Through Unscented Kalman Filter for Data-Driven Leakage Localization in Water Networks. Welcome.
Thank you very much. Okay. So, in the meantime that the PowerPoint starts, I will introduce a bit the paper. In this paper is a joint collaboration that we have for a long time now from our university, in particular the Institute of Robotics, and the Universitat of Bucharest and the Polytechnic of Bucharest. So this work is done by Luis Romero, that is doing the PhD in my team. Okay. So the outline of the presentation is the following. First, I will motivate a bit the paper and the research we are doing nowadays. Then I will introduce the proposed methodology that follows the spirit of the introduction. Then I will illustrate the methodology with a case study from where we will produce some results and discussions. And we'll close the paper with the conclusions. So, well, most of you know about this topic because you are in an invited session devoted to the water management. In particular, the paper focused on the leak detection and localization in water distribution networks. This problem of leaks has been addressed also in some other applications, but in this case, we are focusing in the case of the water distribution systems. In practice, probably you know, but the companies already have some devices, typically acoustic devices, that they use for localizing the leaks. But these kind of instruments are only useful when you have an approximate idea about where the leak is located. So we are not trying to replace this hardware-based solution, but instead we are trying to develop new tools, software tools, that helps in this pre-localization, because the final localization at the end should be done with the standard devices the companies has. So in particular, in the literature, for many years, there has been a lot of research in this topic, in water distribution networks, using models, using the physical model of the network, using simulators, as for example IPANET or others, combining the information from the sensors and the model, using some kind of logic, could be classical FDI logic or more advanced machine learning tools. Some proposals already exist in the literature. The real problem is when you try to apply this in a real network is that maybe the large companies of big cities, they have good models. But in practice, unfortunately, in, let's say, medium or small networks, it's very difficult to have a very precise hydraulic model. Because they have to estimate a lot of parameters, especially roughness and some other physical parameters that are always difficult to get. And if even they get, they do not match with the real behavior. There are errors between this model and the reality. This has motivated, from our experience, to move to pure data-driven methods. I mean, there has been like an intermediate step where still people use models, from these models produce data, and then they apply machine learning. But from our point of view, this is a bit unrealistic because it still requires a high fidelity simulator that in practice, as I said, many companies don't have. They have only maybe the possibility to install a few number of sensors. This is what they tell us. And of course they know, because they have built the network, they have the layout. So this they have. They know at least one map that indicates that the length of the pipes, the interconnections, etc. So our idea is not to use just data alone, like a pure database method that even some authors address, using classical, for example, statistical methods, but instead our idea is to combine the data-driven, let's say, methods with the structural information, the graph, in this case, of the network. But without including in the graph a lot of physical information because it's not always feasible. So we combine database methods with structural information. So in fact, in this line of ideas, in our team, we developed some initial methods where using some basic interpolation scheme. In that case, we were using a kriging approach. We are doing a first approach, then we use other approaches as other people do, trying to follow this path. And in this paper, I will present an enhancement of an approach that we already developed, this student Luis Romero developed, that follows a little the spirit of the interpolation based, but in a more sophisticated manner, as I will present in some minutes. And also trying to introduce in this interpolation method some physical information that we call the graph-based interpolation, because we use not only data, but information of the graph inside the process. And in this particular paper, and this is the novelty of this paper, because this is a little background, is to introduce not only information from the pressure meters, but as you know, in many cities, they are starting to install what are called the automatic meter readers, that are like in the electricity that is more spread out everywhere. You have a digital counter that informs you about the consume. So in water also, this starts to happen. It's not so widespread as in the electricity, but in some cities, in the city of Barcelona, for example, they start this process. So this will allow you more information about the consumption, that is typically the most uncertain information you have in that problem, because you have to infer the pattern of consume based on historical demands or based on the pattern of consume of the zone. And all this creates a lot of uncertainty. So the idea of the approach is a bit summarized here. In fact, this was the first approach I was commenting, that is, we call this approach the GCI. The GCI, what do is a kind of interpolation using just the Laplacian matrix of the graph of the network. So it's not using more information than the graph. And the measurements, in this case, only of pressure in some pre-selected points in the network. So altogether, the measurements from these pre-selected heads in some nodes that should be installed if they are not there, plus the network topology, this interpolation process based on this algorithm there produces the head estimation in all the nodes that you don't have sensors. That's the idea, because the leak localization in this case is producing the head with the current sensors and compare against the case without leaks. So that's the idea. So in the next step, we were improving, as I said in the introduction of the paper, the possibility to use some hydraulic information, for example, the length of the pipes. This is something that is easy to obtain. And this allows to enrich this data-driven model with some hydraulic information. Of course, this is not mandatory. Just we were doing just to see how this enrichment can benefit the interpolation results. Okay? And in this paper, as I said, the novelty is what is in the blue dashed line block. We add to all this already enhanced scheme the possibility of, in some selected nodes, because we have automatic meter readers, we can have an idea of the consumption of the flow. So we integrate all together, and this is the novelty of the paper, with a Kalman filter, a nonlinear one, an ascended Kalman filter, that do the data fusion of the information that already provides this already pre-existing scheme of leak localization based on data and the graph plus some hydraulic information with the measurement of the demands in the nodes. So this will provide, as you will see in the result section of the paper, of an improved network estimation of the heads in the nodes that you cannot measure, and consequently, this will produce an enhanced leak localization result. So here we can see the variables that we inject to the process. We inject the control head, typically at the input of the district metering area, the sector that we monitorize. We have a pressure meter that just guarantees the pressure of the sector. This is HO. HS are the sensors additional sensors that we'll install in some pre-selected internal nodes to the district metering area, and the CA are this consumption provided by these automatic meter readers in the places we have. And all this will provide through this, let's say, unscented Kalman filter, the estimation of the head in all the nodes. So also in the paper we investigate two approaches to estimate these heads. One is based on what we call the static weighting, and a second one where the weighting is dynamic because there is an update using the Kalman filter updating formulas. So after that, we produce some vector of data that include, as I said, all the measurements I was commenting, and here we have the formulas that we use for integrating the information from the measure sensors. In particular, the heads and the demands measured with the automatic reader meters. So at the end is a classical data fusion problem where the measurements are integrated with the updating of the heads I was commenting before. So in order to compare the results, I will show the results that are produced using two approaches. One that we name algorithm 1 here, that is the UKF GCI, just use this integration of the automatic meter readers with the interpolation-based method that use only the graph, with no hydraulic information. And in the second algorithm, here the name algorithm 2, will enrich the method, adding some extra hydraulic information based, for example, in the length of the pipes and some other estimations from the physics. Okay? So to illustrate the results of this approach, we were using an open source problem, because sometimes the difficulty is to share. Some colleagues share the case study to compare, but this is not always doable, because if it is a real network, sometimes the companies do not agree. So we use here a public benchmark that is available, in fact, in the IPANET distribution software. So here this is a quite large network. It has this number of nodes, has two injection of water through 4 reservoirs, and some other numbers that you can see in the table. Also in the figure that you have on the right, you can see the sensors we are considering. We do not consider sensors in all the nodes, because this is impossible. There are some works in the literature that people assumes that you have the pressure of all the nodes. This is not feasible. So here we reduce the number of sensed, let's say, nodes. This is a problem that is not presented in this paper, but in the literature there are proposals of how to do the pressure sensor placement. And also we see here the points where we assume we have the automatic meter readers I was commenting at the beginning. That is a bit the innovation of the work, how to inject in our head estimation scheme the information about the flows in the nodes we measure. So with this idea, we generate some data using IPANET. Of course, we don't have data from Modena. We don't have any relation. So we need to generate synthetic data. So still is missing to do an experiment with real data that we are doing now in another project. We are carrying with a real water network. But this is a preliminary study with this open source, let's say, case study. We generate the data in a synthetic manner using the APANet and using all the considerations that you have in the table. I will not read in detail, but you can see, and in the paper are detailed, where the leak is injected, the size of the leak, the precision of the sensors, and the uncertainties. Since we are in a simulator framework, in reality we don't have to inject the uncertainty, but to make more realistic, we consider some uncertainties in the process of data generation. So, additionally, we design our head estimator based on this approach described in the first part of the paper, assuming that in this particular case we can install up to 20 pressure meters. Still is a lot, because in a real network probably they will allow to do 10 at most. But anyway, for just doing comparisons, it's a simulation problem. We consider that we have 20 pressure sensors and we have 40 automatic meter readers. There are some other parameters we need to tune that are detailed in the paper. Now it's difficult to enter in all the details. So here, with this, let's say, setup of our algorithm, we went to the comparison of the different approaches I was commenting during my presentation. In particular, here we compare 3 approaches. The first one, that is in dark, black, we see the method that uses only pressure meters and the interpolation using some hydraulic information. And this is like our best result up to this point. So here we are trying to see the improvement that we can achieve when we profit these automatic meter readers. With the first approach, we didn't use this information. So if we have the chance, because our network has available these automatic meter readers, we can profit that this extra information is available. So here, using the approach, the 2 algorithms I was commenting that we developed in the paper, we can develop this Kalman filter that produces, in case that we use only structural information, the line that is in this orange, or I don't know the color, maybe orange, and the other one that is in red. So we can see that just with the structural information, adding the automatic meter readers, we improve with respect to the original method I was introducing. So it makes sense to do what we are proposing. And if additionally you have the chance to enrich this method with some hydraulic information, you can even further improve the result. So this is regarding the estimation. So this plot shows the root mean square of an average of the different nodes that you don't have sensors. Because if you have the pressure sense, you have the precision of the sensor. But if you don't have pressure meters in the other nodes, you have to do this estimation. And finally, as I said, all this is with the purpose of leak localization. So the idea is that knowing the data without leaks, we can apply the result. Since the behavior of the network is more or less repetitive every day because the demand pattern is repeating, we can use, for example, data before the day that the leak occurs and after the day that we know the leak occurs. And we compare the 2 maps of head estimations, and comparing the 2 maps, there are several ways of doing. The simplest is using distances, or we can use more elaborated classification approaches. We can see here, in this case with our method that is described in another paper, we provide a kind of probability of a particular node is or presents the leak. So we can see the result in colors. So just to conclude, because the time is limited, if something is unclear, you will ask me. This paper introduces an improvement to a type of methods that are very interesting from the company point of view, because it doesn't require the physical model of the system that not always is available, just using the graph and if you have or not some hydraulic information, and profit the automatic meter readers and the pressure meters that you can install for leak localization. So we have seen that this is an improvement with respect previous works, because it allows to consider the information about the flows that not always is possible. Our idea is to continue this development, doing more elaborated analysis of especially the leak localization part that here was presented in a rough manner. Okay? So that's all. Thank you.
I think in the interest of time, I think we should wait and discuss after the session, because we are a bit delayed due to technical problems. So let's thank the speaker once again. And the next paper will be presented by Christine Verde and is entitled Identification Algorithm for Simulation of Leakage in Pipelines. Should I find?
Paper 2. No, here's the PowerPoint.
2.
Okay, it's
No, it's here.
okay, now we go here. Okay, I'll do it here. Okay, good morning, everybody. I'm going to sit here. I think it's better, especially because I want to move the pointer here on the screen. I'm going to speak today about the identification algorithm for simultaneous leaks in pipeline. Especially the important word is simultaneous leaks. We are assuming there are there are two leaks. And of course, what we know that the leak diagnosis is an important problem, and because there are human errors, the infrastructure sometimes is not correct. There are faults in sector and illegal extraction as well. And I want to make here a difference between two problems. One problem is the distribution network, when there is a leak in the distribution network, as the work that Vincent presented before, and when there are leaks in a main line. Main line with things that are long distance without any branches and without any closed loop or closed feedback in the loop. And in this case, of course, we know there are environmental uncertainty because the temperature, something change, and this change all the things. We have the effect of the corrosion, and we have the effect of onshore and offshore conditions because there are as well pipelines under the sea. And we know that this is a fast-growing market all over the world. And I concentrate in this particular case because it's simple. If we solve this problem, we can go then to the feedback. The feedback the demand is a main problem here in the distribution network, and here is not the case. Of course, we know there are different technology, but I want to speak today, as I said, not consider all the possibilities to solve the problem, but I consider the two leaks identification. Of course, it's rarely studied. There are a lot of methods, completely, I don't know how many papers I get every week, studying the case of one leak in network, but not two leaks in a pipeline. And it's, of course, that is the probability to have two simultaneous leaks, so that two leaks at the same time is not the probability is very low, but in any case, when there are some natural phenomena as earthquake or a hurricane, this can come. That's because this, in a special time, the leaks appear, more than two leaks appear, and of course, as well, when there are some faults in the joints of the lines. And what we think is that the only possibility is really to have maneuvers that help us to identify the leaks, because it is well known that this is not an identification problem if you consider the 4 parameters when there are 2 leaks, because we have the position and we have the coefficients of the orifice of the line. And this is the reason, because if we assume that only measure pressure and the flow rate at the input and the output of the network, of the line, really you cannot solve the problem. This is well known that we can solve the problems. And the outline of the presentation will be the following. First, I'm going to speak about something that is really very important, and that is the equivalent transformation. Because it's now well known that for any number of leaks in a steady state in a model, there is an equivalent model with a single leak with the same port condition. It means if we have the same pressure and flow rate on the extreme, like a two-port system, there is all the time, there is one equivalent model with only a single leak. It means you get, any software get confused because you assume that there is one leak. This means there are two leaks, and for each scenario, there is only an equivalent model with a single leak. It's exactly like in electric circuit happened with the Norton and Thevenin theorem. You can have two circuits with the same behavior, with a P structure and with the star or the Y connection. That is exactly what happened with the water. In this gets confused. Why? If you test every method, design it assuming one leak, when there are two leaks, he gives you the results of one leak that it doesn't exist. It's a virtual leak. You go there and there is no leak there, because there are only a problem equivalent. But this result is very important. 10 years from now, we proposed the first scheme, and until now, not everybody, only my group, consider this equivalent transformation. But it's very important, yes? And from this, what we consider now and we consider that the leaks, that the parameters of the leaks remain constant. It means the flow rate could change, but the orifice, they remain. It means it doesn't occur, they remain. And the other is the leak position cannot change. Even if you change the structure, the leak position remains. And with these two things, we can get a criteria in which we can identify the parameter, assuming the invariance of these leak parameters. This is the important point here in the results. And with this, we get only to show you that help you to identify two leaks, even in an experimental pipeline. Okay, what I say first, the equivalent transformation. I have here the partial differential equation of the system. When there is one leak, of course we know there is a break in there, and if you see the pressure profile, you will see that so long you have, this is the point where the leak is, and you have the pressure here before the leaks, and this is the gradient pressure after the leaks, and this is the position of the leak, and here is the pressure profile. And what you know at this parameter, this remains constant. It doesn't matter if you change the operation point. The pressure will change, but the parameter LF will remain. This means what we need to identify is lambda F. Not QF, it doesn't help you, because it's going to change when you change the operation point. And this is the model of one leaks, and when you go to two leaks, this occurs. And what you can see here, it's very important, something that we miss for a long time. If you see how the pipeline with two leaks behave, you will see that the flow rate at the end, it doesn't change really. Look, I simulate here 4 different scenarios, 2 leaks scenarios, but in different positions. And if you see, the change is in the input of the flow rate. But if you see the outflow, you will see that the pressure, that the flow rate is more or less the same all the time. It means this variable doesn't help you a lot. You cannot recover from this. This variable doesn't help you anything. The difference helps you, but QL doesn't help you from identifiability point of view, observability. You don't see. for 4 different faults, 2 pair of faults, you don't see any difference. Yes, and this you can see here, I have here the pressure profile when there are 2 leaks, and you will see, okay, we have this pressure, we have here another profile, another gradient, and here we have the 3rd gradient, depending where the position are. It means, but if you change the operation point, this graph is going to change, but the position L1 and the position of the other point will not change, because the leaks are there. They cannot move. They change how this triangle behave, but it doesn't change this position. And this is the thing that we are using to recover and to identify the 2 leaks. I have here only the expression of the pressures of the gradients of each of these lines, and you will see here that the gradient between the first and the second leak, there are 2 ways how I can evaluate this slope M2. One is I've used only information upstream of the equivalent line. And there are another way if I do it only using data of the downstream. It means there are 2 ways to try to determine this slope and to determine this M2. And when they are the same, it means that you have the correct triangle. It means the correct triangle corresponds when this measure and this measure match. When this pressure is exactly the same. If it's not the same, it means that you are evaluating a virtual scenario, that it doesn't exist. And with this concept in mind, what we have done here is to say, look here, I simulate here what happened when I change only the operation point in the line, and you will see the position remain, the pressure change in the input, the pressure change in the output, and you will see here, this is the equivalent virtual leaks, this change. And with this small deviation, and this very small, this can help us to identify the exactly leak position. It means I'm going to evaluate this equivalent position using different operation points, one using only data upstreams of the virtual leaks, and another way to measure this, so that to evaluate, estimate LF will be using the downstream. This is why I use U and D. This means I'm using only upstream data, and here I'm using only downstream data from this. And from this, when these 2 evaluation of the LF is the same, then I exactly in the correct evaluation of the two leaks. And from this, of course, I get here 1 residuals. Oh. The difference between the LF that I can estimate properly and using the data of this, and when I use this evaluation, and from this error, when I minimize this error, I know exactly that I found the correct position. And of course, after this, the other thing is only optimization problem. I have to minimize this error, considering, of course, the constraints that the leak position must be inside of the line, not out of the line, with some initial conditions. And from here, I can develop a very simple gradient algorithm. But you can use whatever you want. The main contribution here is that I have 1 criterion in which you really can't evaluate and to know how far you are from the correct position. I show you here the results. We test this in our experimental labs in Mexico. That is more or less 165 meters. And you will see here, this is the line. Just going this way. Yes, and we have the measure here for the pressure and the flow rate. And here is what happened if we consider the synthetic result. This is with simulation only. I hear these bold lines means these are the experiments that we are going to test before. You will see here how run the optimization problem and how far we close are to the real scenario of the faults. And here you say this is for the positions, and this to evaluate or to identify the coefficients associated to the orifice of the line. And if you see here the errors, really they are acceptable. Only in one case, the error is very huge. As you see here, this 16% relative error. And you know what's the difference between this scenario and this for two different, these two leaks, it depends how far there are, how is the difference between the leak one and the second. If the leaks are very close, the error increases. And when the leaks are really separated, the distance between one leak and the other is huge. The optimization is you get very good result. It means really there is a physical constraint that we have if we have both leaks really very close. And here are the results that we have. But one important thing here is I put here a remark here. If you see the flow rate at the output, it doesn't change a lot in one operation point. But if you see the equivalent virtual leaks, they change a lot. Because the information is here, not here. This is the output. I tell you that you don't say nothing. The outflow don't say nothing. And we test now this with the experimental results. You here see the data are noisy. This is the pressure at the input, at the output. On here, you see here are the two leaks. And you have to distinguish between two leaks that are here. This is at one operation point, another operation point, and another operation point. And if you see here how the optimization results, and you will see here as well that really the criteria is minimized. Here's with respect to the experiment 1, and here's with respect to the experiment 2. There are two experiments, this we made in the lab, and you will see here again, the flow rate at the output is more or less the same all the time. But the equivalent positions change strongly. This is for one scenario, and this is for the other. And with this, I go to the results. Okay, what I say, that we assume the important is that we consider that the invariance parameter of the leaks, and the more important is maybe this, the equivalent position of the leak related to the two leaks is highly sensitive to the two leaks scenario, not the output. It doesn't help us. And what we are doing really is we take the advantage of the sensitive of these equivalent leaks. It's a virtual leaks, and this is the main contribution of the paper. And we use a simple gradient method. We are using now another method. Doesn't matter which method you use to optimize the problem. It's a trivial optimization problem. The problem is really to use this equivalent leak position. And we have shown with simulation and experimental data that really we get a very good or satisfactory results. And with this, I finish my presentation. Oh, I close. I hope there is not any question. Let's go to
I think we have room for a short question. Yes, please.
Come to the microphone here because you two have high quality here.
Okay. I had a question here. You say you test 4 different scenarios, no? So this scenario, it was used for the position of the leak or also the magnitude of the orifice?
No. I think when I say this for, when I say this for, okay, you have to.
I think
No, I don't change anything. When I say it in the results, I I change the operation point that you have to get out of here. I say, U2 has the priority. This, we change the operation point only, a little bit, but the orifice magnitude change. It means the orifice remain, the flow rate change, but the orifice remain, because if you have a hold of 2 centimeters, it's 2 centimeters today and tomorrow, it's the same. And this is the same with the position. It means this scenario corresponds to different operation points. It means what we need is to change a little bit the operation point of the line. And with this, you increase the number of nonlinear equations which you have to solve. And if you increase the number of equations, there is a point in which you have the same number of equations than the same number of variables. Then you can solve with any optimization problem. This is a very easily resolved. And you, Jorge, you have another question? For a cut?
An additional link. For 3 links.
Can you repeat the question?
Yes, I repeat the question. They said, what happens if I have 3 or 4 multi-leaks? Of course, you can't increase the number of operation points in order to create the numbers of equations similar, it means equivalent equations to solve with equivalent number of leaks. But every time that you increase the number of leaks, the precision of the results will be reduced. It means trivial from practical point of view.
Good. With that, let's thank the speaker again.
Thank you very much.
And then to the third paper, presented by Leonardo Gomes, on leakage localization in urban water distribution network using LSTM deep neural networks. Yes. The scene is yours.
Is it third PDF? Do I need to press the keys of the... Okay, okay. Don't worry. Thank you. You have to press Control L, I think. Control L for full screen. Yeah. Do I need to press the keys? Yeah. Okay. Good morning, everyone. I'm going to present the results of the paper, Leak Localization in an Urban Water Distribution Network using an LSTM Deep Neural Network. This is the outline I will be presenting, and commencing with the motivation, as was stated in previous presentations. Water distribution networks are really complex systems that are exposed to different factors that cause leaks. And in recent investigations, it has been demonstrated that worldwide, the percentage of water lost to leaks is almost 21%, and in developing countries, this percentage is even greater at 40%. In recent results from some investigations have demonstrated that the top 4 cities in the world with the greatest water percentage loss are located in Mexico, which is the main motivation behind this work. The correct management and transportation of water is a very important issue for all governments and cities around the world. And even the fact that the greatest part of the water distribution networks are buried underground, well, it difficults monitoring and leak localization tasks. The state-of-the-art typically distinguishes between diagnosis methods based on software and hardware. For the hardware-based methods, they rely mainly on the use of different instrumentation and sensors to locate the leaks. However, these methods tend to be expensive and involve a cost factor that is non-viable for all possible applications. From the other hand, in the software-based methods, they rely on the processing of data collected from different sensors and through different computation methods in order to locate leaks. And given the complexity that is associated with the leak diagnosis problem, in latest years, the methods that have been gaining constant interest are related to deep neural networks. And the state-of-the-art typically has demonstrated that the main category of neural networks that are used for leak diagnosis are convolutional neural networks. So the main contribution that we present on this paper is the application of a different architecture, which is the LSTM neural network that has not been as widely used in other research. So simply, as it was mentioned before, artificial neural networks are a mechanism related to machine learning where the learning of living organisms is recreated using a mathematical graph that takes numerical vectors at the input, which are transformed in a sequence of layers, which are called hidden layers, until they reach the output. So in order for be useful, a neural network has to be previously trained, and during this training instance, the values of these intermediate parameters, which are called weights and biases, are adjusted until a minimal error between the actual and the expected outputs of the network is obtained. However, one problem that is related with the common architectures of neural networks, well, it's that they tend to perform poorly when they are processing time-dependent data, which is typically the type of data that we have when dealing with measurements from sensors installed in water distribution networks. So in order to process this kind of dynamic data, we rely on the use of a particular kind of neural network, which are called recurrent neural networks, whose mathematical model is given in equations 1 and 2. And one specific kind of recurrent neural network that has been gaining a lot of interest is the LSTM, long short-term memory, LSTM for short, whose mathematical model is given in equations 3 to 6, and the architecture is presented on figure 3, where new gates are introduced in the architecture of the network to control the flow of the memory. So this allows to link distant time steps in the data, which allows for a more precise analysis of the different dynamic behaviors of the data that is being recorded. So in this paper, the objective was to implement the leak location system using a real-world case scenario, which is the one that we present here. It's a district metered area, which is located in the city of Madrid, in Spain, that consists of 312 nodes, which are interconnected using a 14-kilometer long pipeline. Water is being constantly consumed at 44 different nodes of the network, and 10 pressure head meters are installed. And also, the system is fed from a water reservoir, which has a near constant elevation head, and his outflow is also being constantly recorded. And leaks are experimentally recreated at one specific node, which is the one in red colored star shape, letting water out of a fire hydrant. However, given the complexity of the problem, because the system is huge and it's actually very large in size, sectorization in 13 different zones is proposed to reduce the complexity of the problem. So the proposed sectorization is the one that is presented in figure 5, where nodes that are located geographically closer present a similar leak signature and thus they are clustered together. And actually, in a real-world implementation, this would greatly improve the results when dealing with the pinpoint, with the exact peak point of the location of the leak. So some measurements are collected for a period of 3 days in the experiment that is presented in figure 6. This corresponds to a real leak scenario where during the first 2 days, the system operates in a nominal operation. This means that it has no leak. And during the last day, a leak is induced at the node that was previously mentioned. And once the transient effects of the leak dissipate, the leak outflow remains almost constant. And this dataset is collected at a rate of 1 sample at each 2 minutes of measurements. However, one main problem that is related with leak diagnosis tasks is the lack of sufficient experimental data for the training of the deep learning models. And thus, an EPANET model of the network is used to synthetically generate new data sets for all the possible leak locations, and most importantly, for a leak-free operation, which is, well, the EPANET model is very popular, both in industry and in academia-related work related to water distribution networks. And to emulate as realistically as possible the demand habits of the users of the network, the proposed demand pattern is the one presented in figure 8, where it can be seen that throughout the day, the demand habits of the users vary differently. Whereas in late night hours, the demands are typically at their lowest. The highest demands are associated with the afternoon and the evening. However, this operation of the system cannot be replicated exactly day by day. So we expect to find some kind of uncertainty in the value of the demand multiplier at each time instant. So in this study, we propose that this uncertainty can vary between completely ideal 0% uncertainty to a maximum of plus minus 25% for each time instant, which is the way in which we are recreating different demand habits for different users. So the proposed methodology is the one presented in figure 10. In this methodology, the nominal demand pattern of the network and the nominal demands are first contaminated with a random uncertainty value, and these uncertain demands and demand pattern are considered as the input for two simulation instances of the hydraulic model. One that considers leak-free operations and one that considers the leaking model. Values for the pressure head and outflow from the reservoir from the two models are obtained, and the residual between them is computed. Then these residual values are contaminated with a random uncertainty value as well to emulate the measurement noise, which is intrinsic to real-world sensors. Also, each data set that is generated synthetically using the APANET model is labeled according to the sector where the leak takes place is actually located. And these uncertain measurements are used as the training inputs for the recurrent neural network, and the training targets are the labels, the categorical labels that are related to the occurrence of the leak at each node. The proposed neural network architecture is the one presented in figure 11. First, a sequence input layer of dimension 11, which is same as the number of training instances is used. 11 because we have 10 pressure head meters and 1 flow meter at the outflow of the reservoir. Then an LSTM layer is used with 24 hidden units, which is the same as the length of the training instances. Because I forgot to mention, the simulations are performed for a duration of 1 full day at a rate of 1 sample each hour, so 24 samples in total, considering that the leak takes place after the 12th hour, simply to emulate the behavior of the leak, that first it doesn't happen and then it happens. So to emulate that behavior, datasets are constructed in that way. After the LSTM layer, a fully connected layer is used to transform the outputs of the LSTM layer into an adequate format for classification. Then a softmax layer computes the probability of belonging to each of the categories, to each of the leak categories, considering 14 in total, which are 13 related to the sectorized clusters and 1 extra category, which is labeled as 0 for the leak-free conditions. And finally, a classification layer takes the final decision about the leak category. Simply for reference, that was the hardware and software that we used for the training of the network and the training hyperparameters. And as it can be seen in figure 12, we present the training plots for the recurrent neural network, where it can be seen an evident increase in the accuracy of the trained network as the training iteration pass, as well as a decrease in the loss. So several training tests are performed because, as it was expected, different levels of uncertainty were considered. So in total, we performed 6 training tests, and well, the performance metrics, which are accuracy, recall, and F1 score, are presented in table 3. And as it can be seen, significantly good results are obtained even under uncertain conditions. Finally, for the experimental validation, the same dataset that was recorded in a real-world scenario of a leak is used. Simply, we perform a resampling of the data from one sample each 2 minutes to one sample at each hour in order to be consistent with the data that was used for the training of the network. And to compute the residuals for this real leak scenario, we use the synthetic datasets that are created under a leak-free condition to compute the residuals, which are presented in figure 14. And after the experimental validation is performed, it can be seen that, well, the real leak scenario corresponds to a node that is located in zone 4, as it can be seen in figure 15. And the training test, the validation test was performed all the 6 trained LSTM neural networks. In 3 of the cases, the predicted sector was wrong. And in 2 of the cases, even if the predicted sector is wrong, which is located in sector 5, it is still physically located close to the real leaking node. So in terms of actual distance to the real leaking node, these results, well, are considered as correct. And in finally one of the cases, the sector was predicted correctly. Finally, some conclusions. In this paper, we presented real leak diagnosis results using a real world water distribution system as a study case, considering a sectorized representation of the system. And this sectorization was presented given the similarity in the leak signatures to the clustered nodes. Even if the neural network was trained with synthetic datasets generated using a hydraulic simulator, these were contaminated with various degrees of uncertainty to consider realistic demand habits. Results are presented both for experimental and simulation conditions, and in future implementations of this work, we should further analyze the sectorization in increasing the granularity to locate ideally leaks to a node level, and in addressing the problem of multi-leak diagnosis. So this is the presentation, and thank you very much.
Any questions?
It's not a question. Have you tried to simulate 2 leaks simultaneously in a network? What happened? Because I agree there's going to happen the same that we have with a line. It has to be physically.
Okay, for everyone, the question was if I have tried to simulate 2 leaks simultaneously, and the answer is yes. However, the clear effect is that they cannot be as easily as separated, because two leaks happening at the same time translate in simply more leaked outflow from the reservoir. So the outflow from the reservoir increases, but there is no actual way in knowing which are the nodes where the leak is occurring. So that's the problem that happens.
We have a benchmark for the next 6 months now.
Approach here because I have to pass the microphone. I've got a very, how to say, specific question to a given scenario. So let us imagine a football championship and a match, Germany against Mexico, and no one is using water for 90 minutes. What will be the behavior of your system in that case?
Well, I mean, that is a very valid question, because actually what was being kind of represented in the uncertain demand habits is that as much as that kind of behavior, that nobody is consuming water for a certain time, we can also have like the scenario that, for example, in one very particular hot day, everyone is consuming more water. So it would be incorrect to assume that more consumption of water is related to a leak. So in both scenarios, I think we try to like emulate in these plots, because, for example, in some of the instances, in the uncertain plots in figure 9, the demand multiplier at some time instance is lower than the actual expected value. So by contaminating the demand pattern with a random plus minus value, we consider that water can be consumed more or less. And since the performance metrics of the trained neural network was able to locate the leak even under those uncertain conditions, we can assume that, as far as we know, the system will still perform correctly.
Is
share. And please, Jorge, put your slide here.
The memory.
To close this. Escape. Now put your,
In the memory.
put in the memory.
You have the memory.
Ah, yes, I give you the memory. Okay, we go now to the fourth, this is the fourth session, the fourth talk, and the name of the talk is the extended Kalman filter-based algorithm for two simultaneous leak diagnosis in pipelines. And Jorge Delgado from the Universidad of Valle de Mexico is going to present the talk. Please start it, Jorge. Take the microphone.
Thank you for this presentation. Good morning to everyone. I'm going to present my project, my work, entitled as Extended Kalman Filter Based Algorithm for Two Simultaneous Leak Diagnosis in Pipelines. The contents of this presentation is a brief introduction, then the leak diagnosis strategy. After that, the experimental results, and finally some conclusions. This figure that has been already used for Leo is very important because we can see that the average of water losses in some cities is a very complicated problem, in particular for cities in Mexico. As you can see, Mexico City, Chihuahua, San Luis Potosí, and Tuxtla are the worst cases, reaching up to 65%, in particular for Tuxtla. Scientific community has studied this problem, and from different approaches, including model-based approaches, fault-sensitive and artificial intelligence-based algorithms, and the characteristic of the leak problems that can be summarized in the type of pipeline, as mentioned before, single pipelines, branched configurations, and networked systems. And the kind of problem is, as mentioned before, single leaks and multiple leak problems. In this case, for example, if we consider the single leak case, the problem is that we can identify the magnitude and position. And this can be done by using, for example, a simple state observer that works well in steady state. However, this is not possible for two or more leaks. In this case, the observability condition doesn't hold, and we can use a persistent input to distinguish between those states. The contribution of this work is that by considering the simultaneous leak problem, it represents still a challenge, as mentioned before. In this case, the solution is proposed based on an extended Kalman filter. However, we can take into account that persistent signals, in the case of an observer, can cause additional damage, such as new leakage events. That means if to solve a simultaneous leak problem, the problem is that the use of no constant inputs can cause additional leak scenarios. This is the problem. the leak isolation strategy is to use an observer which requires a model of the pipeline, which is derived from the well-known Water-Hammer equations, and this couple of partial differential equations must be discretized by using, for example, definite difference method. If we use this method, we can obtain a couple of ordinary differential equations for n number of sections given by equation number 5 and 6. In scenario, the discretization model can be represented by this figure in which we can see all variables that are involved. And those equations correspond to this, are described in this slide from variable Q1 until Q3, including the effect of the leak in the positions Z1 and Z2. Then the idea is to identify those values to have the position of each leak, but also the magnitude given by the value of lambda 1 and lambda 2 in equation number 7. This system can be also in which the state is given by those variables Q1, H2, Q2, H3, and Q3. In this case, as we are interested in identify the position of each leak, those parameters can be extended as new state variables. In this case, as given in equation number 9. Those parameters are considered as constant value, with constant value, and we can extend our original system to another one having 9 states, which is presented in this equation. So the idea is to design an observer for this state, including the coefficients of the leaks. As mentioned before, it's not possible to identify the whole state by using a constant input, and is in this case necessary to apply a persistent input. This input ensures that we can distinguish between all initial states of the system and allows us to identify the whole state. In this case, this signal can be like a sine wave form, which is enough for our application, which ensures that at the outputs of the system, we can distinguish we can distinguish all the states of the extended system. So the extended Kalman filter can be summarized in this slide. The observer form is given by equation 14, and all Kalman filter equations are presented in table in this table. The experimental results are presented right now. We used a pipeline located in Sinvestab, Guadalajara, in Mexico, and it's a single pipeline which has one. So to implement the persistent input, we apply the controller of the pump upstream, extreme, in this form to move the flow rate inside the pipeline in like a sine form. This was the frequency of the pump to produce the or persistent input. 3 experiments were performed. The prototype starts to operate in a leak-free condition, and approximately at time 70 seconds, this couple of valves 1 and 3 are opened, producing the leaks at position Z1 equals to 17 meters and Z2 49 meters. After that, once the leak starts at 95 seconds approximately, the persistent input starts. That means that between the leak occurrence and the application of the persistent input, there is a time in which we don't have the application. Those experiments differ each other from the initial conditions and the nominal flow rate. In this figure, we can see this, the pressure head at both ends of the pipeline, the pressure head at upstream. It starts about 20 meters and downstream about 10 meters water column. In this case, only one frequency is in the signal, and it produces this behavior in the flow rate at the ends of the pipeline. As we can see, once the leak is present in the system, for a short period of time, we don't have the persistent input. For the Kalman filter, the covariance matrices of measure and process noises are given by equations 16 and 17. This is the initial state for the experiment 1, and the estimation of the leak position for leak number 1 and leak number 2 is presented in this figure. As we can see, once the leak appears, this couple of leak appears, and the persistent input is not applied, the divergence in the estimation is evident. But once the persistent input is applied, the convergence of the states is better. You can see that even we don't have an exact location, but we can say that these results are acceptable. In this figure, we have the magnitudes of both leaks, but in this case, we don't have comparison with real values because it's not possible to measure the coefficients. This coefficient is related to the discharge coefficient and the area of the hole of the leak. For the second experiment, this is the initial state, and in this case, this is the estimation of the leak position. Once again, we can see good results, and this is the estimation of the leak magnitude. In this table, we can additional information about an additional experiment that doesn't appear in this presentation, but for the experiment number 1, the error was the lowest, 5.4 4% for the first leak, and for the second one, 5.7%. The worst case was the treat experiment for which the error was about 12% for the first leak and 15% for the second one. As conclusion, I can say that a persistent input has been designed and implemented to locate two simultaneous leaks in a pipeline by using an extended Kalman filter, and the location was achieved accurately, but some difficulties regarding convergence were observed. The third leak case, the third simultaneously leak case, was not possible to solve. This is because the input requires maybe a combination of more than two frequencies to ensure the observability of the system. Finally, as a future work, high-gain techniques will be investigated in future developments with practical implementation purpose. Thank you very much.
We have a couple of minutes for questions. There are some questions. Yes, Marius, please.
So in practice, you don't know how many leaks there are.
Of course.
1, 2, 3, or 4. So
Please repeat your question. Repeat the question. Yes.
Yeah. So you understand the question? In practice, you
Yes,
don't know how
in
many
practice we don't know a priori how many leaks are present. Yes, this is a very interesting question. From now, I don't have an answer to face this situation because often only we have the measurement at the ends of the pipeline, and in practice, even most of cases, there is no records of the behavior of the system. Only we have a very short period of time with measurements. In 2016, I had an experience, a real-life experience, and the first hypothesis was that only one leak was present in the system because it was impossible to apply a persistent input for a real pipeline. This is the problem of this research. Thank you.
I have another question. Which boundary conditions are you using in your system? Because you say that you only move the input, the pressure of the input, and if the output is a fixed constant, then the behavior that you showed you, it doesn't realistic. They move both, the input and the output pressure move, and this
Yes.
is not the case if you consider as constraint the input and the output pressure.
Yes, this is the input and the output pressure.
Yes, but
both.
this is what I say. If you in the boundary, in the partial differential equation, you have two boundary conditions fixed. If you have the H output, why change? If there's a fixed output, why?
This is it's not possible to keep the upstream boundary condition with this behavior and the another one with like a constant.
Why
It's
not if you,
possible.
or how do you have the physical?
Because the pressure moves the flow inside the pipeline.
But
and-
you have two boundary conditions.
Yes,
The flow, I know, the flow will change,
yes,
but the pressure, the
Yes.
output pressure
But
has to remain constant. If this is the boundary condition, you fix.
yes, but in this case, the behavior of the
It
system.
means that in your installation you have something else. Because in my installation, if I change the input, the output remain the same because it's the pressure of the air. At the end of the pipeline is the pressure of the air. The pressure is the pressure of the altitude.
Yes, maybe it depends where the sensor is installed. In our case, this is the behavior of our system.
But you have this as well
But
for
only-
simulation.
No, this is real data.
But you have as well for this. It doesn't matter. Okay. Let's go to the next speaker, and thank you very much to Jorge. Now we leave Mexico and then go now to Denmark. Now I'm going to introduce two. You are the first one.
Yeah, first.
Bulut, who do you pronounce? Bulut Kushman from Denmark, and he's going to present topological data analysis based replay attack detection for water networks. Now it's different, an attack. This is important now.
Yes.
How is the difference between an attack and a fall? But anyway.
Yes. Hi everyone. So I'll try to utilize my time as much as possible. Thank you for the introduction. So today I will talk about topological data analysis based replay attack detection for water networks, which is together with my supervisor, Rafael, which is the work of together with my supervisor, Rafael Wisniewski, and also Karsten Kalezo, which just happened to be the chair of the session. So here's the outline of my speak. I will give a hopefully brief introduction, and then I will talk about some preliminary information about topological data analysis, and I will proceed with problem statements of introducing the replay attacks, and also the water networks, which we used in our simulation. And then I will continue with explaining the methods and also giving the experiment results, and then conclude my talk together with the future works. So basically, cyber attacks against water networks are became a huge problem, and one of the difficult attacks to detect is called replay attacks. And in our work, we focus on an alternative approach for replay attack detection, which is basically formulating an anomaly detection problem for water network sensors. And our anomaly detection scheme basically relies on topological data analysis, which I will refer to as TDA most of the times throughout the talk. The reason TDA is chosen, so why we use TDA, besides the fact that I'm very interested, is basically there are some works that shows it can capture periodicity for signals, so that we assume that also replay attacks may produce some periodicity. TDA can capture it, and this will be done by using topological features that I will also explain in a bit. And the right ways to do is basically choosing the right window size and dimension for your signal, which is going to be a time series. And of course, we need to have some like numerical numbers or like some sort of ways to apply this topological information for our anomaly detection scheme. And in that case, we will use Betty curves for topological feature as a topological feature representation for anomaly detection scheme. And this will be done to compare the nominal and attacked measurements. So now I will talk about, hopefully, not to bore you much with TDA, but it is basically focuses on an algebraic homology, and it observes the continuous deformation, some under invariant changes. So basically, what it does is basically analyzing the shape of data via topological features. And topological features I'm talking about is basically how are they called is, let's say, zero-dimensional features are going to be connected components, and the loops will be one-dimensional features, and voids are two-dimensional features, and n-dimensional holes are just n-dimensional holes. And connected components, you can. If you focus on the figure on the bottom, connected components refers to the mass of your shape, and the loops will be, let's say, the holes inside, and voids. It's not in the picture, but you can imagine it as either like a football, like there will be some air inside. You can imagine. And on the figure on the left, you have one connected component and one loop, while the figure on the right contains two loops and one single component, one single connected component. And let's say if you take the figure on the right and split them apart in the middle, then it means that you will have two connected components and two loops. And also, a good thing about TDA is that you can also apply it on a univariate time series, but you need to apply some tricks. So you need to, by the help of a sliding window, you have to map it to a higher dimensional map. That is with the dimension of m+1, hopefully. That m is an integer, and delay can be a real number based on your time series. And this, with the help of this sliding window, you can form point cloud data, which you will apply TDA on top of it. And now, the important part is we need to apply a filtration, which is going to be the main method to capture the topological informations. So as I mentioned, we will apply the filtration on top of point clouds. And how it is done is basically, as shown in the second bullet, is we're gonna attain a ball to each of these point clouds we obtain, and that will have the radius, let's say lambda/2. The filtration process goes like this. So for each point, we will increase the radius at equal amount of time for each of the points. And then we need to observe the interaction, the behavior of these points within each other. And this will generate a homological group for each dimension. As I mentioned, we have like 0 dimension, 1 dimension, or n dimension. And this will contain topological features, as I also map it to as connected components and loops. And based on the interaction, these homology groups will have birth and death as defined. But in practice, so this is how it looks. So in the figure on top, the left is the first step of the filtration, where we assign balls to each points, and then we slowly increase the radius of each ball at the same time. And we just keep doing that, and so on. As you can see, the first one, let's say we have 50 points, and we assign, let's say, very small radius to each of the points. And this will represent, I will have, let's say, 50 connected components and 0 holes. But as I increase each radius, those balls will start to interact with each other. And 2 balls touching each other means that one of the, let's say, 2 balls touches, and which means that one of the connected components needs to die. So one of them should kill the other one if each of them are touching together. And if you have enough balls touching each other and they're forming a hole inside, that will form that means representing a birth of one loop. And if you increase those balls enough at a time that they will just merge, then it means a death of a loop. which is one-dimensional topological features. And for this example, I have two representations for topological features. One of them is persistence barcodes, which is basically shows that so the red ones are basically connected components, and it shows about their persistence, which means when they're born and when they're dead. And also blue ones represents the one-dimensional, which is the loop, and it, as you can see, it born around 0.25. And this x-axis is obviously radius, the amount of radius increased. And then also, at some point, loop will die if we increase the radius of the ball big enough. As I said, so what I show you was like persistence information representation as persistence diagrams and barcodes, and you can also have some other representations. And for our work, we focus on using Betty curves, which is basically the sequence of Betty numbers for filtration values of lambda, which was our value for radius. And Betty curve means basically at a certain lambda value, how many, let's say, if Betty number, if the Betty curve of 0 dimension, if I would like to get at the filtration value of lambda, I just need to count how many connected components are there. And thresholds can be formed on top of the Betty curve definition, and of course with respect to lambda. And what we use for our detection, I'm gonna say metric, is basically the absolute integral of two Betty curves. And then I will quickly give you an introduction for replay attacks. So basically, I have the nominal measurement signal defined as that, and let's say hacker tries to apply replay attack on top of the nominal measurement signal. So hacker basically starts recording at time tr, and it stops recording at ts, and it starts to repeat the same signal that is recorded. And this is the water distribution network that we use to simulate our data we applied. So we have 672 samples for both nominal and animals data. Sampling time is 15 minutes, and simulation time is 1 week. And what we used for this experiment is the tank level of the first zone, which is illustrated in here. And then in here we will inject the replay attacks. And also for, let's say, measurements noise, we just add a normal distribution white noise added to the signal to emulate a measurement noise, which has the variance of 0.01 meter. And we have like 4 scenarios of replay attacks that is rely on the length of the recorded signal. The very on top is 2 hours, and below you have the 6-hour replay, and then 12-hour, and a day. And it's obviously, yeah, the 2 hours signals is more repetitive. Repeating the smaller time in a more frequent way, which is sort of obvious. But if you focus on a day, it is more sort of disguised. And the setup for our persistence analysis is for capturing the periodicity, we need to use double of the natural periods. And for this case, we use 14 as our embedding dimension, which means that the Fourier analysis tells us the natural period of of the simulation signal is 7. And delay of the sliding window we set as a 1. And then with this setup, we apply our filtration, which is on the next. So this is the filtration step of 2 nominal signals that relies on the same simulation, but with a different noise, different arbitrary noise. And here are the Pearson's diagram of the connected component and the loops of two nominal measurements. And as you can see, so for our case, we will only focus on the loops because that's sort of where the periodicity information is captured. And you can see the loops are looking quite sort of similar, not exactly the same, based on the different noise, the same noise, but like a different measurement. But they have like some similarities. And then we focus on the first dimensional Betty curves of that two nominal Betty curves. And both of them are considered as normal. And we apply the thresholds, which was the absolute integral of those two. And this is the threshold value, which is somewhere around 0.97. And then we apply the same procedure, same persistence analysis on all of the scenarios. And as you can see, all of them are actually different from each other, so giving the different one-dimensional topological features nearly. And then when we take one of the nominal Betty curves and compare it with the Betty curves of all of the attack cases, and we can see that they're quite different from the nominal version. And then when we apply the metric we use for our thresholds, and all of the cases are just exceed the threshold. And now I would like to conclude this talk as the introduced method is basically relying based on this setup of attacks. It successfully detects. So it roughly takes 3 minutes to generate those Betty curves. It's not really a problem for water networks because it's quite slow. But if you need a detection system that requires a little bit faster, let's say maybe seconds or milliseconds, then it's not that useful. But of course, for our future work, now we are working on applying some online updating persistence to overcome this issue, and hopefully taking the detection scheme to seconds. And also, we would like to test some different triple attack setups, which can be maybe more in disguise or maybe non-detectable than our case. And yeah, thanks for listening. Yes. Any questions?
I have one question. Do you think you can apply this for stall? Is the people stall water? Because
Stall?
stall. They take it out as. Yeah, if some people, you assume you tank, and assume that some people put a valve there, and they took now a couple of liters of water, and tomorrow
like a leakage detection.
it's not, but it's not a leakage because they stall and they stop it, and after a while appear again.
I see,
It means when you make a leak, for me, it takes forever because so long you don't repair, the leak is there. But when I say to stall the water, because in my country the people stall the water.
Okay.
And if you can apply these kind of techniques, it's not it's an attack. In some sense, it's an attack.
Yeah.
It's illegal action.
And then I think it will be like appear in the tank level or
Yeah, something else. It means
something else. Like as long as it appears in the
line is you can,
yeah.
you come
Okay.
to the bank and then you
Okay.
an illegal branch. Let's go to
Oh,
say
I see.
this. Maybe it's the correct way.
Okay, so initially, like before replay attacks, I actually apply it on the leakage detection part, and it also like detect it. But for that case you're mentioning, if it, I would say if it's gonna appear on the measurements of, let's say, attack, or maybe somewhere else, some other sensor measurements, I would say it has a good chance to detect, but yeah, maybe I need to apply it first. I don't know. Thank you.
Let's go to the last speaker. Let's come I think now Karsten is going to present the last talk about cyber attack and fault detection using a digital twin of the controller software.
Yeah, this guy here.
I'll give you the microphone here.
Yes, thank you. Yeah, this is some preliminary work I have done together with my colleague Rafael Wisniewski. He's from Aalborg University and I'm from a company called Grundfos. And yeah, this is the outline of the presentation. And I will start with some introduction to what we have thought about. So cyber attacks is becoming more and more on the agenda in water utilities. In the case that people can attack the control systems especially, and therefore destroy real systems, not only the billing system, the access to their bill information. And we think this is really an issue, not only for the water utilities, but especially for all the systems that are infrastructures. This includes the water utilities, which is a small picture of a small system there. At the same time, we would like these systems to be easy to operate and to be optimized. This means that today most systems are connected via a SCADA system where you can access all the controllers. Normally this SCADA system is used for reading out data so the operators can see what happens in the system and also to set information down if they want to change some parameters in their operation, so they're able to set down new parameters, references, control parameters from this SCADA system. And this is also maybe the mean or the place where most optimization is placed when you're going into real life utilities. They put it into the SCADA, and the SCADA then calculates the new set points to all the controllers in the system and operates more optimally. But when we do that, we also introduce a vulnerability in the system, because now we have one point of access to all the controllers. In the old days, each of these controllers were placed out in the system, and you had to go there manually to change something. Now you have one point, and you can destroy everything from that one point. So this is the issue we are addressing here. Beside that, many places has what they call bedside SCADA, meaning that they have a computer at home. When they are caught due to an error in the system in the middle of the night, they can start acting on that already from home. But this means that there is an access from outside into this OT operating control system. And this is in fact also something that is addressed or have been seen in the world. Here this is an example from a water utility company where there was a former employee where the access to the operating system was not closed, so he could get into it and destroy their water cleaning system. And we also have maybe a more severe. I have marked this because this is not a political agenda. It's just to say that outside access gives the possibility to destroy things, and there are also real-life examples on that. So our idea is that all of these local controllers, we have the software for these, so why not use that in some way? And the idea here is to use that for a system that can detect changes to these software settings. And then the idea is to place this digital twin of the control software on a third-party cloud somewhere, third-party computer, such that the utilities do not have access to it, such that you cannot go in and manipulate from the utilities side. So if you have a former employee, access in different ways. So the idea is this is a typical control system where we have the controller and the process, and we take just a copy of the control software. But this means that our control software, the only way we can access the control software is via the measurements that they would have taken from the system itself. And it produced output system. And we would like, in this first try, we would like to use an observer-based approach. But observers, when you do the design of these, you need to have access to all the internal state in your controller, or in your process, in this case the controller. So we have split up the software a bit, such that we have access to the internal states in the software, these set tilde there. So this is the basic idea. Then just a few words on how we have then done it. First of all, we assume that our controller can be described by a switch affine system where we have discrete dynamics in the first equation and an output equation acting on different domains. Then we are dealing with hydraulic systems, and we always have nonlinearities in these hydraulic systems, and often we can add a nonlinear function on the output and thereby make gain scheduling that makes the control more stable, or stable in a wider range of operating points. So we add this gain scheduling function. Here we assume that there exists an inverse of this gain scheduling function, and then we can apply that to the actual control input we read from the system, and we can get back to our original affine switch system. So this is our starting point. We assume the software can be described and put into this form. So this is our starting point. The dynamics of this system is normally not stable. If you think about a PI controller, it's not asymptotic stable. It's in this case has its poles on the unit circuit. This means that if we have some initial conditions that are different from what we expect, they will stay there forever. So we have to do something with feedback, and this is where the observer comes into play. And we have just used a standard observer, taking a copy of the system, and then calculate observer feedback gains. And different observers for each domain. Then we have restricted ourselves to say that the domain of the output equations and the domains of the dynamics are the same. And we assume that we can identify in which domain the system is from the measurements on the system. That is the U and the K's, the Y's measured from the system, and the U's output from the controller. Then we can set up some aerodynamics, and we can design stable feedback gains for each of these domains, such that the system is stable for any switches between the domains using this LMI. Really standard methods. We have applied this approach on a simulation of a small water network. So this network with two pumping stations where the controllers in the pumping station are equivalent, and they are controlling the pressures into the system. So they have a reference pressure to each of the controllers that controls the pressure at these points. And these pressure references are designed from the utility side such that there is a service pressure inside the network that is always kept, and such that the fraction of water taken from the two sources are split in a way that is suitable for the utilities. We assume this is put into a control setup like this, where we have a 4-layer system. We have a physical layer where we have our sensors and actuators, a control layer where we have these local PLC, local controllers at the pumping station, a SCADA layer that has access to these controllers, and then a supervisory layer, which is the one that we design here. We place so with the SCADA layer, we open up for these attacks that I talked about in the start. And we propose to place this digital twin in this supervisory layer, where we are collecting data via smart gateways. So we put a gateway locally that is not connected to the controller, that can transmit data to our digital twin via a communication diode. So we are not able to send data back, meaning that attacks on our supervisory layer will never be able to destroy anything, but we can read all the data and thereby do fault detection. These data, when we have collected them, they could also be used for standard fault detection in the system, and this is also what we'll show here. But first, the digital twin. The controller here is a standard PI controller, but with a kind of a gear shift. So you have a controller that controls the speed of the pumps in the pumping station, and if the speed exceeds a certain limit, it gears up by starting yet a pump in the system. If the speed of the PI controller drops below some value, it stops one of the pumps, and in that way change the gear of the system. And we can put that into our setup with these affine switch systems with these two equations. The first equation, the dynamics, the first raw in that is just the standard integral action in the controller, and then second line is what you do to avoid wind-up problems in the controller in the case of saturation in the controller. And then we have domains, one for saturation and one for normal operation, and then one for each of the number of pumps operating in the system. So these are the domains, and the output equation is just the output of the PI controller and then the saturated value of the controller. And we end up in having a bunch of domains that can be identified by N, with how many pumps are running, and then if the speed is in saturation. Then we can build our observer, just by taking a copy, as we talked about, and we can design L using the proposed LMI approach. As I said before, we will also be able to detect failures in the system, and here we have just to show that this is in fact possible. We have designed a small burst detection approach using the same data. This means that we are for the digital twin, we are collecting the pressures, control pressures. We are collecting the speed and output from the controller and the number of pump outputs. So based on that, we should be able to design a burst detection algorithm. And what we have done here is we have said that this is a centrifugal pump, and this is a good model of a centrifugal pump. And from the two first equations there, we are able to calculate an estimate of the flow. It's not very precise, but it is an estimate of the flow. Then we can use that estimate of the flow to create a model of what we expect of flow using Fourier built into a Kalman filter. So we get a prediction of the flow, and then using standard techniques we can compare these two, and then if there is a change in the flow, then we will be able to see it in the trivial, and to avoid noise we have added a QSUM algorithm. We don't have a very precise flow estimate, but this is not necessary because we are comparing to what we have seen before, so these possible errors in the estimate of our flow is just mapped into our model, and therefore we can still compare them and see a change in flow. Then some simulation results. We have run a simulation on this small network example, where the first plot is the pressure. The red and blue is from the controller, and the yellow one is the service pressure inside the network. Likewise, with the second one is the flows. Then we have the number of active pumps, the speed, the attack detection signal, and the leakage detection signal. And here we first applied a burst of around, I don't know, 5-10% of the maximum flow when the flow is high. And we can see here that the QSUM start to grow, and at some point it detects the leakage. It's not very fast, but it do detect the leakage. But it's also when the flow is high, so therefore it typically is difficult. And we are not using a flow sensor. And then to the more important stuff, then we have an example where we have a change in the reference that will, you can see on the blue and red curve in the second plot, that the split of flow from the consumption or the production plants differs, and therefore this will destroy the production plants or overlook one of the production plants. But we can immediately detect it when this happens. Then we have a case where we have changed KP, which increased the number of starts in the system and therefore will destroy the pump when continuing operating, and we can also see that in the residual. Then the KI value, and again that increases the number of starts, destroying the pump, and then we have a minimum speed that will mean that we cannot control the pressure correctly, and we can also see that. So this is kind of the results that we obtained, and then some concluding remarks. This work is primarily on using this digital twin, in particular for water distribution network, but I do believe that it can be used elsewhere also. The digital twin setup here is assuming that the system is a switch linear system, a switch affine system, which I'm not sure it's always the true, but this is what we have here. And numerical tests have shown that in this particular case, we are able to detect these attacks on the controller parameters. But I started to say that I wanted a system that could use a one-to-one copy of the software. This is not the case. We have to open up the software and rewrite the control in a form such that we can use this observer approach. So future work would be that figure out how we can design a feedback that can ensure that we get good residuals, even though we don't have access or don't have to split up the software in a new way. And then I'm not sure that this particular setup we have is covering all type of controls, so we also need to investigate that further. Thank you. I believe this is we have called it a digital twin because it's a copy of the software, but we have designed an observer. So the digital twin should just be seen as the process model in the observer in this case. So normally when you do an observer, you have a model or a copy of your process which you use to estimate the states in your system. And here we use this software package from what is available from the software developers.
Okay, so the digital twin is replicating this software?
Yeah, exactly.
Yes.
Okay.
Exactly. And then we need the feedback because this is typically not stable. It's magnetically stable because it's typically PI in some way, or at least integral action.
Some other question? Yes, another question.
I get confused. The digital twin is replicating the software. It's to clear how the software can be replicated.
Yeah, you are totally right. Because this is exactly what I addressed before, saying that here we still have some work. So we have the process here, and we have the software, the controller software here. But we have written the control software, so we can easily take a copy of that and put into our supervisory layer here. So this is what we call the digital twin. But we cannot use the software one-to-one, in this approach at least, because we don't have access to the internal state in the system. And we have integral action, so we need to some way feedback to get rid of differences in the initial conditions between the two software packages.
any question, I close the session and I invite you to go to the lunch. Let's go to give a applause to Carlos and to all the This is mine. Okay, take this.
And all the papers here, it's
All the papers
throwing
were
them
there.
all
All
around.
we have to do
This is how normally it is.
we have to
to this afternoon session about prognostics methods and predictive maintenance. I will be chairing the session. My name is Marcos Quinones, and I am a research scientist working at Vanderbilt University in the USA. We have 5 presentations today, all very interesting, and each one of them will have 20 minutes. You should take 15 minutes for the presentation and 5 minutes for questions, just to try to have some interactions. And I would like to welcome the first presenter for physics, for the work titled Physics Application. Yes, it should be here. So you are... Okay. So... Oh. Yeah, so this first work is titled Physics-Defined Hidden Markov Models for Reusable LPRE Bearing Remaining Useful Life Estimation, and the presenter is going to be Federica Galli. So, you're welcome.
Thank you very much for the introduction.
We need it for the YouTube.
Okay. Thank you very much for the introduction. Sorry. Welcome everybody. Thank you for following this session and following my presentation. Today I'm here to present you a portion of the findings I obtained during my PhD thesis. The work I'm presenting you today is funded by the French Space Agency, CNES, and the region of Normandy. So here's the plan of the presentation. I'll start by describing the research context and the study case that we selected, and then I'll move on to the proposed methodology, the simulations, and the results. So the research context is the scenario of reusable launchers. We imagine that we have a launcher that performs its mission, and the first stage it's coming back on Earth. At that point, we perform some data collection. We collect all the mission data, and then we use it for prognosis analysis. When we say prognosis, we speak about the estimation of time to failure and risk for one or more existing and future failure modes. Once that this analysis is performed, we imagine to pass on the information to who is planning and performing the maintenance so that the launcher, but in particular the reusable rocket engine, can be requalified for the next mission. So we focus on the rocket engine. You can see here a simplified scheme of the propulsive system, and since it's a very complex system, we decided to first study the turbopump bearing. So what we propose to do is to estimate the remaining useful life of the bearing that is inside the turbopump there with a data-driven approach that uses bearing vibration signals and hidden Markov models. So the methodology that we propose is divided in two parts. First, we have unsupervised training, and then we move on to algorithm exploitation. In the unsupervised training, we collect all the available data, which in the rocket propulsion field is unfortunately not that much. And then we treat the signals with the wavelet decomposition. We calculate the HI, the health indicator. We have to transform it a little bit because hidden Markov models require a discrete health indicator. And finally, we can perform the training. When this is done, when we have the HMM model, we collect the new signal, the signal from the performed mission. We treat it in the same way, and finally we can compute the remaining useful life. So what I'm going to do right now is give you some details about each step, and then we will look at the results together. So here you have a scheme of a classical ball bearing. We collect data with the accelerometers. Here you have an example of a vibration from a healthy signal, a healthy bearing. Nothing is affecting his functioning. If degradation appears, we can see it. For example, here we can see that it's healthy at the beginning, and right after, the amplitude of the signal starts increasing. Of course, this is a qualitative analysis. By looking only at the raw signal, it's difficult to go further. This is why we have a procedure to go until rule estimation. This procedure continues with the wavelet decomposition. So the signal we have here is decomposed up to level 3. So we go from one raw signal to 8 subsignals in blue. And for each subsignal, we compute the relative energy, which is the selected health indicator. And is basically the energy of one of the subsignals divided by the energy of the raw signal. After that, as I was saying, we have to discretize the health indicator. So what do? We discretize by intervals, and we obtain something like this. The first thing we can see is that there's a loss of information. Right now, it's kind of difficult to identify the moment of failure. So, for the training data, we use the DCS statistical test to find the failure instant and improve our discretization. In the end, the health indicator looks like this. What can we see immediately? It is very easy to see where failure happens. And if we can see it, the hidden Markov model will be able to see it also afterwards. So for the algorithm, it's going to be really easy to understand where is the failure, so over 20, and where is the degradation, below 20. Now, hidden Markov models. We are speaking about a stochastic model that is based on some states in orange and the transition between the states. So we describe the dynamic of a random variable in this way. Since we can't observe the states, we have some variables, some observations in green, and we have to establish the probability of having a certain observation given a certain state. And everything, all the probabilities we can compute are grouped in the transition matrix and the emission matrix. Now, it can be a little bit difficult to grasp at the beginning, so I have a little example. This is Paul. Paul is a friend of mine. He lives in a city where it is either rainy, either sunny. And during the day, he has a simple routine. He goes walking, he shops, or he cleans. And his activity is chosen according to the weather. Now, he really likes to tell on social media what he's doing. He never tells how's the weather, but thanks to HMM modeling, we can actually deduce if it's sunny or rainy. The simple HMM of the example is here. We have the hidden part, the weather, and we have the observed part, so Paul's action. In our case, what's hidden is the bearing degradation, because we cannot stop the engine and look inside the bearing. And what we observe is the health indicator. And we can go and train the model to have the probability, like the probability that Paul is shopping while it's rainy, the probability that we have a certain indicator when the bearing is damaged. Last detail about our model, it's a physics-defined model. It means that our states were chosen according to a qualitative degradation model. In the model we have degradation stages that are reproposed in the Markov chain. Why do we do this? Because we want to minimize the parameter to learn afterwards. We don't have a lot of data, unfortunately, so we need a model that is as small as possible but still representative. And finally, we can compute the remaining useful life as the absorption time. So the time to go to one of the transient states to the final state, the failure state from which we cannot exit. If we arrive here, we have arrived at the end of life. There is a very interesting mathematical formulation which is based on two matrices, and by computing the ratio of the determinants, we obtain the absorption time. It's quite efficient, especially for small matrices, like in our case, and all we have to do is introduce a time counter to estimate the remaining useful life from the absorption time. Why do we do that? Because the Markov model can tell us in which state we are, and if we ask to estimate to decode what's the state every time instant, it can tell us, okay, you have been in S2 for 5 minutes, but the estimated time of absorption is always the same. So we have to take into account of the time we already spent in one state and subtract it to obtain the remaining useful life. Now, let's move to the computation setup. So we had a data set of vibration signals, but the uncertainty, especially with respect to the failure instant, was really high. So we decided to prove the concept with a set of synthetic health indicators generated with this profile, where we know very well when failure happens, because it's the parameter T3. And so we defined the initialization matrices, and we used the Baum-Welch algorithm to train the HMM model. Now, let's look at the results. Here you have on the top one of the generated sequences, number 22. You can see the profile I was showing right before, with the increasing slope and then some increase of the variance here. Then we have here the results of the DCS statistical test. So you can see that the test clearly finds the failure instant when the variance increases. And at the end you have the discretization. So you have in blue the discretization by interval, and in orange the discretization with the failure detection. And now, on the right, you have the estimation of the remaining useful life. So we can see that at the beginning it's underestimated, and after 60 minutes, the HMM can correctly estimate it until the end of the bearing life. I have other two examples. Here we can see that the rule is correctly estimated since the beginning, but failure is is estimated too soon. Here it is overestimated, and failure is predictive a bit sooner than expected. Why do we have these results? Well, since our HMM is physics defined, we can interpret, we can give a physical meaning to these results, which is the following. The HMM during the training learned the most probable degradation dynamics. So if now we give it a signal that it's faster or slower in its degradation, it will overestimate or underestimate the remaining useful life. Here we have this, because this signal was slightly faster than the learned dynamics. Before we had this, because at the beginning this health indicator had a degradation that was a little bit slower than the degradation that our HMM learned. So all these results were to prove the concept. We were asking ourselves, can we actually well estimate the remaining useful life? And what we could see is that yes, we can, but we have after to give the correct interpretation of our results. So to conclude, we propose data-driven approach for bearing rule estimation. This approach is based on an optimal HMM structure, which is interesting for us because it allows us to physically interpret the results and to reduce the size of the model to be learned. And it has a quite good prediction capability. This particular method has been amplified, and we recently published a paper about a larger HMM, which has a better performance than the ones I'm presenting you today. The future perspective is now applied to real vibration data, but we're working on that because it's not that easy to retrieve. So thank you very much for your attention. Do not hesitate if you have questions or remarks.
Thank you for your presentation. So questions from the audience? Maybe I should.
I did have one. So the remaining useful life you're computing is some expected value, right? In reality, what will happen is depending on how the system is used, right, the remaining useful life will change. So in other words, say if you rotate your bearings much faster, they'll wear out faster, and different times you rotate them at different times. So how do you take that into account?
Thank you very much for the question. Yes, indeed, the remaining useful life is affected by the bearing operating conditions. This is why in the new model that we have proposed, we have multiple HMM chains that are able to capture different degradation dynamics. And the model can select at the end of each mission what's the best degradation or the degradation that best fits the complete history of the bearing life. And with respect to that, we are thinking about some additional signal processing like angular filtering so that we can actually normalize our vibration signal and take away the effect, for example, of the rotating speed. But indeed, here it was just to see if these kind of HMMs could indeed predict our remaining useful life. Thank you for the question.
Does it mean that you should actually increase the number of parameters that you are considering for the prediction?
Yes. In this case, the number of parameters was really, really small. But as every machine learning approach, it's really utopic to have such small number of parameters. What happens is that even if we increase the number of chains, we are still able to train the chain where we need it. And so still with respect to other approaches in deep learning or in encoders, we still have less parameters to train than other approaches. And given the really reduced amount of data we have, we are still exploring this direction. Thank you.
Any additional questions? Well, I have one question for you. What was the motivation in the first place to use hidden Markov models in a context where you have so many variations of deep learning models?
Indeed, that's a very good question. The issue with deep learning is that from the perspective of the rocket propulsion field is that you lose a big portion of the physical interpretation, which is important to keep for two reasons. The first reason is that it's a very complex system, so it's important to still know what's happening, and also because everything we do is to be given to who's planning the maintenance, so for them it's more interesting to have an indicator or the remaining useful life of a specific degradation or possible damage in the system. They can use that better than a virtual indicator that later has to be linked to the physical degradation in the system anyway. That was the main driving requirement.
I had a related question, which is, in general, you will have to learn of the states of the agent, right? Because when you operate them under different conditions, the states will not be constant, right? You're talking about multiple chains.
Yes.
You could also have multiple states. So
yes.
what are methods by which you can learn the states of the agent?
That is a very good question. We did try some chains with more than 4 states. We realized that with the health indicator we have so far, at a certain point, maybe 5 states could improve somehow the results, but more than 5, not so much. So for the moment, we stayed on 4, and even in the more developed methodology, it's chains of 4 states. But yes, indeed, it's a compromise between the number of states and the number of chains.
Thank you so much.
Thank you.
Thank you, Federica, again, for the presentation.
Thank you very much.
Well, let me welcome the next presenter, which is Cristina Verde from UNAM, Mexico. She's going to be presenting the work, an integrated monitoring system based on deep learning tools for industrial processes.
I can do it with the microphone. Let's wait.
Okay.
No, I'm going to do it here.
Okay.
Okay. Hello, everybody. This work it has been made with my colleague from Cuba, and this, I'm now here really the presenter. And what we want to speak is about how we can integrate cyber attack and false in a monitoring system. This is the motivation of this work. And base it, of course, on deep learning tool for industrial process. My talk is divided in 4 topics: motivation, the proposed method, a case study, and the results. Of course, as everybody knows in this conference, the SAFE process, there are a lot of relevant infrastructure all over the world in which there are a huge amount of parameters and in which we really would like to know to distinguish between false and cyber attacks, because for the society play an important role to distinguish these two cases. And of course, the first things I want only to remember is that we say, okay, what we understand for cyber attack is any type of offensive maneuver generated by a human being or their software that target industrial control system or directly the process device. And of course, the false, that they are desviation of at least one property of this parameter of the system of the acceptable region, and it could be also as well an unexpected change in the operation of the system. And what we know that the advantage of the data-driven methods and that they can deal with uncertainty data, that leveraging the information stored in the SCADA is there. It means we know that we have a lot of data, and what we need is really to take some advantage of this information. And that's in the case for the data-driven methods, we don't require a priori few or only a few knowledge of the process parameter, and of course allow to train to generate patterns and forecast as the case previously presented. And of course that we know now that because the accessibility of the internet of the things on the industry and data technology, really we can improve the monitoring of the systems in reality. And according with this, we think, okay, we know that the deep learning methods are divided in different, and we are going to consider in this work that we have a supervisor deep learning method instead of a semi-supervised, and in particular, we have a recurrent neural network, and in particular, the long short-term memory. This is the particular deep learning method that we are using to monitoring and to distinguish between leaks and cyber attack, and that is possible. Of course, what are the advantages from the long-term shared memory? It's one of the most effective deep learning models for sequential data processing, and its memory can store information for a long period and retrieve it over long sequence. And it is suitable for tasks that involve remembering past. These are the advantages why, this is the reason why we should take the LS term memory. And what we are doing is say, okay, let's go to divide the data. We have the data online, and we are going to have a set of historical data. From this, we begin this from a process. And from this, we go first to have offline a learning process in which, as every deep learning procedure, we have to train data and validate data, and from this we can train a supervised LSTM system, and from them, what we say, okay, now it's going to work online, and we consider this now the data online really to recognize, normalizing the data, and from this we classify the experiment or the data, the real data, in which condition we are, and from there, of course, what we have to do is really to consider if there is, in this classification, because we have the information of this, if there is a fall, if there is an attack, a cyber attack, and we have a normal operation condition that it could happen as well, and we had an unknown condition. And what we said is that if we have an unknown conditions, we have to separate this data and to classify as a new event, and this will go here, okay, this will go here. Again, and store this are historical data, because it means that this is a new event that the historical data has to classify and to work after with the offline procedure. And making this, we apply this procedure really to the case study of the Tennessee Eastman, that is well known, and the plant is divided in 5 different components. This is the reactor, the condensator, the vapor liquid separator, the product stripper, and the compensator. We have there 41 measurements, and we have 11 manipulated variables. And if somebody wants to see the data, we have here taken this from this website. And what we are saying is we have a network with 52 input layers with the same size as the number of input signals. We have dry layers, hidden layers, with 52, 40, and 25 units are considered for, according to some other work that we considered as Geo and Leo from 2018. And we have 3 dropout layers between the LSTM layer to prevent overfitting. The classification scheme was a fully connected layer of the same size as the number of output. Classes are considered, it means 7 for the normal operation conditions, 3 for the false, and 3 for the attacks. And we include also a softmax layer that assigns prediction possibility to each class by a multi-class program. And based on this software layer, the output layer classifies finally the event in fall, attack, normal condition, or an unknown event. The experiment we have made is we simulate 3 specific falls, similar with 3 normal operation conditions, and we consider the 3 has to be with the condensator and temperature in the system, and we consider for the attack the sensors. That's because they are easily to be attacked, the sensor. It's more easy. We consider for the training 500 observations for each of the conditions, and as well we consider for the testing 960 observations as well for the 3 possible class of conditions, that is the normal, the fall, and the attack. And according to this, the data for each fall, attack, and normal condition are really a huge amount, 1,000, 75,000, 25,000 for the validation, and 96 for the testing. And these are the results that we get. We compare with another, no, here is only not a comparison, here is only what we get when as you see here the prediction class, and as you see here for the normal conditions, the classification is perfectly, but as well for other, especially for the attacks, there are some reduction in the sensitivity of the system. You will see here as well with some faults, it's correct in average. And if we compare with other methods used for attacks, because usually the people consider 2 different proposed, and the contribution here is really to say I don't need to have 2 different classification methods, that we can have one single method that's in particular for these 3 faults and the 3 attacks, we can have a single algorithm, a single system which separate the 2 events. And you will see here how well they made the classification for the fault 3, for the 9, and the 50, the classification percent, and as well here for the attack. And I go to the conclusion, because really the impact of the work is really to say that we don't need to consider a separate problem, that we have to consider as a single problem integrated. And we have this in a single algorithm. But what we say is that offline training, we have seen from the experience that the offline training is a very important stage. Really the problem is if you don't have the data separated and training in the correct way, the classification is going to be wrong. The main problem is really to have enough data with the conditions that you want to have it. This is really the issue with this kind of algorithms. And I said, in particular, we use this long, short-term memory as a classification tool to predict the state of the process with noise and with external disturbance. And the results or the comparison with the scheme with other diverse classification algorithms was satisfactory. And of course, another thing important was that we were able to detect new events and to store in the history of the data, and then the deep learning algorithm is going to continue working so long new historic or a new event appear, he starts to learn this new characteristic. And with this, I go to the finish of my talk.
Thank you very much.
If there are some questions, I tell you, my author is there in Cuba, but anyway.
Thanks a lot for the great presentation. I have a few questions, actually. I'm not totally convinced about the separation between attack and fold, if you can explain.
Sorry, I hear very poorly. Let me see.
I didn't get completely how you distinguish between fault and attack. If you can clarify in the real life how you can distinguish between these two events. And also, which type of data are you using? Because normally when we talk about the fault and attack, the big issue is that the data are totally unbalanced. We have a very few numbers of realistic event of fault and attack and an impressive number of normal operation. So I'm just curious about the quality of the data that you have and how you distinguish. And in case, which attributes in your data set are more characteristic for attack and for default?
You know, as I said here, you know, if you see, I assume that this happened because we have the attack are completely a different event from the false. And in this case, it works. The problem is if you don't have enough information to distinguish. And this is the reason because I put in the conclusions that the offline training is a very important stage. If you don't have information from the beginning for the network, he couldn't learn because these events are not. This is the key. For me, this is the problem with if you want to distinguish, you need to have event attacks and faults, and events that distinguish between both. If there are some fault in the sensor, and I am consider that the attack is in the sensor, I'm not going to distinguish these two. This is true. This is what we have.
Thank you very much for this interesting talk. You talk about labeling of the data, and I would be interested in how work-intensive this labeling process is, because as the aforementioned speaker already mentioned, you only have, typically you have few examples for faulty data, and how do you incorporate this in a workflow that is that you can handle using humans, for example, that have to label probably.
You know, they are doing simulation. All the data what they have, and they put some noise in the model. Okay. They have the model. Of course, this is not the reality. For me, this is far away from what we really need to achieve, because really, with simulation, all the methods more or less work. The problem comes with fault detection for me when you want to go to the reality.
But it would make sense to incorporate this into a real-life monitoring systems where you can also specify some rules to automatically label normal data or maybe a text that you know about, and then you can build up a data set that can be used.
This is a problem, and I think that this work really only shows that it is possible so long you have this offline training very well done. If you don't do it well, all the contributions disappear.
congratulations for the presentation. And I have a question. I have a fault.
Yes.
So I know it, and I use the LSTM in order to detect it. My question is, can I use the LSTM to understand why the fault is occurred? There is some information that LSTM gives, and I can use this to understand why the fault is occurred.
Yeah, the reason I think, okay, let me go back. When we have here at the beginning this. Yes, I think that the property that he has with the long memory and the short memory, this help a little bit that maybe you forget events that they are really very old and you remained with the short, and contains only the short memory in sometimes. And even the attack, sometimes they are not permanent. What they do is they put an attack and then disappear, and again, 20 hours later or something like this, they come again. It's mean a fall is there and they don't disappear so long you don't repair the equipment. But the alarm, they do it, it's exactly what they do it when they stole something, petrol or something, that they stole a couple of days and then disappear, and after a while they come again and then come again, and this is, for any method, it's difficult to know how one fall disappear, but the attack could disappear. This helps a lot.
But can I store the sequence that...
yes.
Okay. Using the sequence I can...
Yes. If really what you have is the sequence. The important is you have to look for methods in which you have sequence and you have say, it's not possible that this fall disappear. And the attack is there and then disappear and then come again and disappear. Something like this.
Thank you.
Okay. Maybe a system have if different part of the system connected to each other. In attack, you use a part of a specific part of the system, but in fault, all of them connected to. Because, for example, in attack, you change the values of the data in sensors, but in faults, you have a part of system and it's propagation in all of the system. So the system works.
Thank you.
I think, let's go to speak of the third
Christina?
talk. Yeah, thank you very much. And I think, let's go to try to see if the third author is here. You are here, okay? Please come on, put your slide here.
You are...
Okay, let's go to put your slide here. Okay, let's go here. Okay, let's go see. You are Fatih?
Yeah, that's my last one. First
which...
It's in the folder. Give me a minute. There we go.
Okay, then maybe I take now the session and because you are the next Martin. Okay. Okay, then I'm going to introduce now the third speaker. What do you want?
A pointer.
The pointer is, let me see here. Here is the pointer.
Thank you.
It's up to you, how do you want? Okay, I have the third speaker, and he's going to speak about the sustainability in semiconductor production via interpretable and reliable prediction. And I think that Fatih is the speaker.
Yeah, that would
Okay, thank you for the presentation. Take the microphone.
Thank you. So welcome to this presentation. On behalf of my colleagues from RWTH Aachen, Zurich University of Life Sciences, and Hitachi Energy, it's my absolute honor to present our results on an Unife project. So it was an industrial project in collaboration with Hitachi Energy, where we were working on semiconductors to basically decrease the scrap rate and increase the efficiency. So first, we realized that the control doesn't work. No, it doesn't. But anyways, so I will go through oh, perfect, thank you. Okay, so I will go through the content of the speech. First, I will go through the introduction, what we're dealing with, what's the main motivation,
and then I'll talk about the research questions, what we actually tried to solve in this research project, and then the preliminaries, so you have a good grasp of concepts used in this paper. And then I will talk about the proposed method, what are the innovations, what are the main points that contributed to this paper, and then I will talk about the results, and finally the discussion and the conclusion of our paper. So let's start with the fact that we are now in an age that we are fairly advanced with data acquisition from different industrial assets, and this is basically thanks to Industry 4.0, where we can gather an abundant amount of data from different production assets. And this would basically pave the way for us for basically sustainability and technological transformations that could be used in product quality predictions, predictive and preventive maintenance. So basically what we are discussing right now in this conference is the very foundation of these advances is based on Industry 4.0 technologies. And in domain of quality prediction of the products, there are many industries that are trying to basically detect early signs of quality deviations because they can have a lower scrap rate and have a more sustainable production. So lose less material and use less energy in the end. And then, as I said, that is very, very important nowadays because we will have to have sustainability in productions. We have to prove that we're efficient and we're not basically wasting any raw material during our production. So one of the industries that is heavily investing on this technology is the semiconductor industry. And they are basically focusing on more complex production lines nowadays. There used to be single stages in the industry. Now we have multi-stages in the industry where we are basically having more complex production lines and much more data to work with, higher dimensional in a way. And the problem we have in this industry is that the limitation of data and accessibility to data is very delayed because many methods are basically trying to use the entire information from the process. So imagine you have a couple of stages in your production, and the methods that are normally trained and used in academia try to rely on all the information you have from the whole production line. So as soon as you're done with the production, you try to do the prediction if you are going to have a successful production or not. So that could be a bit of a delay in your prediction. You already have used your raw material, you already have gone through the production, you have used energy, so that's quite a problem. And for many industries that are opting for basically sustainability, that would be not quite efficient because you have to detect early signs of quality deviations as soon as possible. So that's a key point that we try to focus on here. So we have to detect those deviations as soon as possible. So in this paper, we'll try to answer three main questions. First of all, how can I use the accumulated information that I have from the production line? So as the production is going on, I have more and more information about the processes, about the parameters. How can I integrate this information in my model? And how can I basically have calibrated models that I will define later on to have them correctly showing the certainty they have given their predictions. So just because I have an accurate model, it does not mean that I have a good model. It has to be reliable in a way that when it says I'm 80% sure that this prediction will be a sample of a good production, it actually should mean 80% and not some random number. And then how can I come up with a cost-effective modeling for my predictions in a way that as I'm gathering more information, how much does my accuracy actually increase, and somehow in a financial point of view justify the increase in accuracy given the information I've got from the production line. I will show the figures as well. So the preliminaries are quite simple. So as I said before, for many applications, specifically safety critical systems, your models that are data-driven have to be reliable. That means your prediction certainty have to actually mean something. And you could achieve this potentially by calibrating your model. And in a binary classification, in a very simple sense, it is defined as follows. So imagine you have a classifier F, and then you'll have your input space X, you're mapping it to your target space Y with two classes of positive and negative because it's binary. And then you say your model is calibrated if for any arbitrary probability value between 0 and 1, your empirical, basically, probability value is equal to your predicted probability value. So that's the definition of having a calibrated model. So imagine if you plot your predicted probability values against your empirical predicted values, you will have a line at 45 degrees. So that's what we're trying to opt for. I will show the figures also later for this concept. And how you can basically achieve this as a post hoc calibration for your model. If your model is not good enough, you can use sigmoid calibration. So it's the best performing one. There are so many ways, but in this paper, that was the best performing one. It does not mean that it's the same case for your use case, but that's what you would do. It kind of looks like a logistic regression in a way, that you are basically trying to adapt your kind of the sigmoid function that is giving you the probability values, right? So you are basically changing your intercept and your slope in a way. So think of it that way. You're putting another layer of computation on your classification model to have prediction probability values actually meaning something. And about the production line, so it's a production line in Lenzburg in Switzerland, and there are basically 5 stages we studied, and there are some stages that are not monitored. So we did not have information from those given stages of production. So from the first 5 ones, we had information, we had sensor readings, we had all the information we could have, but the rest was not accessible because it was a new production line, so there were not many sensors installed yet. And we had basically 3 test units trying to show if the production is going well or not. And the most important one for us was the final product quality test. So that gives you insight if you are producing something good or not in the end. So that is what we're mainly focusing on, but just a general overview, that's how the production looks like. And there are different processes that have to be repeated somehow because there are so many sub-processes in those processes. So one process in this project is one production asset, and different sub-processes are different things you could do with the production asset. So think of it that way. And then we had some problem with the data. So as you expect, industrial data is highly unbalanced. And because it's the beginning of the production line, the number of samples that actually were failing were much higher than the ones that were not failing. So that was new. And then we had also changes in the test unit result interpretation. That means your criteria for fail and pass given a test result would change because the crew staff at ABB, as the Hitachi, was gathering experience how to interpret those results. So that was also another source of uncertainty. We had missing information from numerous processes, so as shown as the gray block here. And in the end, we had so many external factors impacting the production. So we had raw material changing, we had the vendors changing. Those would basically impact the production as well without us knowing, because those information is basically not logged anywhere for us anyways. So what we go through is the following. So we first prepare the data. That would be separating the sub-process data. As I said, one process is one production asset, and sub-processes are the things you're doing with that production asset, right? So we had to first go through the data in the table and divide those, find those, what they mean. We had to clean and annotate the data because they were not necessarily connected to one another from different tables. So we had to clean and annotate the data, given the information we have from different stages and different test units. And we had to do pre-processing. For example, we had to encode categorical data, the nozzle ID, the recipe name, etc. And then, as soon as we were done with the pre-processing, we could start with model training, which is basically structured like this. So if you remember, we said we have 5 stages we have information from, right, shown here. And then per stage, we have 3 test units we want to predict. And if you remember from the last figure, stage 5 is after the first test unit, so it does not make sense to predict the result in your previous, production asset, because your model would be non-causal. Your model is relying on the information from the future. So that's why we did not put it there. And afterwards, we ensemble all the predictions we have from these final test unit results, and then calibrate the model to basically have prediction models actually meaning something. So that's the basis of this paper, is how it looks like and how they're basically created. And then for the base learners, we have gradient boosted trees. We have used the XGBoost library, pretty common. And we have used grid search to find the perfect parameterization for our model. So it was not like hand-tuned. It was just tested with all the possible values we thought could work, and then the combinations of those. And then we also weighted these samples, so we have, in a way, compensating the impact of unbalanced data by sample weighting. We did not undersample or oversample because they were like industrial data. We did not know if that would be a good idea. And then we also had this stepwise training to see how we can increase the accuracy. So this is the result for predicting the result of the first test unit given the information from only stage 1 and 2, stage 1, 2, 3, stage 1, 2, 3, 4, and all of them together. So as you can see, is the number of features we had, the sensor readings that we had, quite increasing through time. And this is basically the accuracy. So you can see if you use only the information from the first stage, your accuracy is quite high, 84%. And then if you merge the information from first and second stage, your accuracy goes down quite a bit, around 1%. But you will have about 20 more sensors used here. So that's how it basically the trend looks like. So how your accuracy is impacted by the information you have from the production assets. But the most important one we want to focus on is the last one, because this is the end result of the semiconductor production, and we want to have this as high as possible. So as you can see, the more information we gather, the higher the accuracy would be, and that is something we try to focus on. We try to come up with combining, basically ensembling these models that we've trained to give another boost in the accuracy. So that was the first idea we had. We tried different data combination methods. And then, yeah, I will go through it real quick now. So for the ensembling the models, we have used the production success probability values. That is easily said, the probability values that is predicted from the simple base learners. Right? So we have different, per stage we have one probability value, and we combine those to come up with a better test result and map it to the very last test unit we have in the production. And then we do not quantize information, so we do not lose the information we have. So it's kind of like knowledge distillation, if you're familiar with it, that you're using the logits from the neural network, but there we do not have a neural network. We just have the probability values directly from a tree. So we're combining those probability values instead of combining the quantized values, zeros and ones. That would not give us information. We will lose so much. So that is what we're trying to do basically here. And then, as soon as we stack those information, the probability values, we try to use it with logistic regression for a couple of reasons. First of all, it's simply interpretable. You know how these values are being combined. Second of all, it has good reliability characteristics. Reliability being the probability value actually means something. And as you can see here, we try to combine the probability values from the last 3 stages for the prediction of the last test unit. And as you can see, the 3rd stage was not important at all for the logistic regression model, and then the 4th and the 5th stages were quite important for it, and in the end we had an intercept. So that's how this ensembling works. So we had probability values from 3 classifiers, which are predicting the test result for the last test result in the end, at the end of the production line. We get the probability values, we combine them, we make a vector, as shown here, and then we combine them given these basically coefficients and this intercept, and try to predict somehow a more reliable probability value for the success rate of our production. So I hope that makes sense. And what happens is you can see the impact of model stacking. So if I show you this graph for model reliability, that is quite a bad model, I would say, because your model is constantly saying, I'm around 50% sure if it's going to be okay or not. But you do not expect that from a good model. You want your model to be quite sure. So, hey, I'm 80% sure, I'm 90% sure that this is going to work. But if it always says, yeah, 50% I'm pretty sure it's going to work, so that would not be very helpful for you. So we try to improve that by model stacking, as you can show here. given the characteristics from the logistic regression, you can see these are more spreaded in the basically probability values, and then for a perfect model you would have this blue line almost on a 45-degree line here. So that will be, this line that I'm showing right now will be the perfect calibrated model, and this is quite a bit off, but that's what you would get given the industrial data, given the noise, the uncertainty you have in your model. And then we pass this stacked model through sigmoid calibration. And then, as you can see here, the number of data points that are between 40 and 50% got less, and the data points that are between 80% and 100% and 0% and 20% got more. So why are these two bins more important? Because you have two classes. If the value of probability is close to 0, it means it's the other class. If it's close to 100%, that means that you are in the correct class, right? So you have to have two bins at around 0% and around 100%. So just to give you an intuition how these distributions should look like if you have a well-calibrated model. And then this is the results of using different calibration methods and the accuracy and the binary estimated calibration error here. So as you can see here, the base learner was the gradient boosted trees that we talked about. The accuracy was 73.32% with the binary ECE of 0.159, but by stacking and also calibrating, you can get your binary ECE much lower, so you increase your reliability compared to your baseline. And then as a side effect, you have almost 1% increase in your accuracy. So just imagine you have a semiconductor production line, you have a very high throughput, that 1% could actually financially mean something for you. So not only you're increasing your reliability, your predictions mean something, you're also predicting quite a bit better. But there's a couple of things I want to go through before ending this talk is, so the lower the binary ECE, the better, of course, and the higher the accuracy, the better. But the issue that we have is we did not have much data from the production line. Normally, you have your training data, you train your model, you have your calibration data that you calibrate your model with, and then you have your test data that you test the whole process, the whole pipeline altogether. But here we did not have enough information to do that, so we use the same data used in training for calibration, and that introduces bias through model. So if you have enough data, please have a separate set of data for calibration so you would not have this introduced bias. So you are increasing your reliability, but you are decreasing your accuracy. So as you can see here, the red ones that have lowered accuracy is because of the fact that you're using the same data we use for training, for calibrating the model. So I will go through the discussion and really quick. So interpretability and reliability are quite important, especially for having the models accepted industry. Industry wants explanation. Industry wants you to tell them why the model is working the way it does. So focus on those things. And then we have so many uncertainty issues that we have in the production line we have to consider all the time. And then that's why stacking and having these gradient boosting ensemble models would substantially help us reach those methods. And as I showed, we had increased accuracy and reduced binary ECE values. So those are the promising results of our paper. And in the end, we want to see the impact of working condition changes on the probability values. So that's another paper I'll be presenting next week, in 2 weeks. So if you're interested, do let me know. I can give you a paper that shows how your working conditions impact your probability values and how you can use that probability value to tell the operator something changed in your production. It does not mean that your system is not working fine, rather environmental or internal parameters change that your system is still working fine, but that's a new region of data for the model. So with this, I've reached the end of my presentation, and we look forward to your questions.
I think we are ready. Okay, I think we have time for one or two short questions. If there are some. Nobody? You spent your 20 minutes again. It's okay. And then with this, I am going to give the next applause and continue. One question, is the last presentation, the author of the last presentation are there? You are here? Okay, then let's go to D later, but come here with your keyword,
With the drive.
with the drive. No, you don't
No.
have. You have to use the computer.
Take this presentation time
Take
to
only
put
the
it.
presentation. Only I want to know
Yeah.
that we cannot take more time.
Move it to a flash drive if you can, and then bring the flash drive.
Okay, now I'm going to introduce the next speaker. I think that Marcos is going to give the speaker, and it has to be with the comparison of transfer learning techniques for building energy forecasting. They come from the University of Vanderbilt in USA. Please, you have the microphone, Marcos. Okay. I go with my watch.
Okay, have to give the talk here. Okay, everyone. My name is Marcos Quinones. I'm going to be presenting this work called Comparison of Transfer Learning Techniques for Building Energy Forecasting that we jointly worked on. Chancita das Charma, Austin Corsi, and Cotton Bis was also here. The outline of the talk is this. I'm going to talk a little bit about the motivation and background. I'm going to discuss the problem formulation very broadly, discuss the case study we're considering for this work, the methods that we compared, that we analyzed, the results that we obtained, and some conclusions. Well, the main motivation for this work is that buildings account for around 40% of global energy consumption. And then creating models that allows you to understand how energy consumption changes with time based on physics is a very complex and time-consuming task, which has motivated the field of data-driven methods to go and create all these models which can be extremely useful for different tasks such as anomaly detection, fault detection, and even prognostics. We therefore try to analyze a critical aspect of data-driven models, which is limited data. When you have limited data from buildings, let's say that you have a very good energy prediction model that works for one building, and you want to use it to leverage its advantages for predicting energy in a different building. Could you use some transfer learning techniques, which is a field of machine learning that tries to leverage knowledge from previous data-driven models and improve the newly developed models in the sense that you need less data to achieve the same performance? That's the question that we are trying to address. So we revised the existing literature and we found that most transfer learning research associated with building energy prediction relies on simulated data or consider only exogenous variables as inputs to the model, such as external temperature, humidity, temporal information. On the other hand, for the energy prediction of building energy systems, there are some physics-based models that have tried to make this prediction based on measurement data from local components. But they have not studied the potential of transfer learning. Therefore, we formulate these questions. How do transfer learning techniques perform when we use real internal measurements of the HVAC systems for energy prediction? That's simply the question that we try to address in this work. And the motivation for it is that we have real data from real buildings, so we can extensively try how these approaches perform. A bit on the theoretical side, I'm not going to dive deep, but this is the basic formulation. In the transfer learning domain, you have a formulation of a domain that consists of a feature space and a marginal probability distribution, which represents the dynamics of your system in this context. And you have a task. Basically, in the task, in this particular case, we're just trying to solve a prediction problem. Therefore, we have a set of labels. And then you have a function, a learn function. And the question that, the problem that transfer learning tries to address is how you leverage knowledge from a source domain and use that knowledge to improve your accuracy in a target domain. I'm gonna talk a little bit about the building and information that we consider. We have two university buildings in Vanderbilt. One of them is called Engineering Science Building. It's used for research and teaching. Has temperature control laboratories. And we have a different building called KISAM, just the acronym, And it's a residential building. It's used for different purposes. We have a set of internal and external measurements, and we have temporal information. Therefore, all this data is what we are going to consider for running this comparison. This is a picture of each one of the buildings, and it has some extra information in terms of the facilities, the different spaces that they contain. So all the experiments that I will be showing are based on real data. Going to talk a little bit about the methods. After extensively revising the literature, we tried to select the most popular and mostly used method that had a sound background in terms of the definition. And we selected 4 initially, and we remained with only 3. The first one is called long short-term memory plus a dense layer. And what you try to do is to fine-tune that memory, neural network memory architecture based on the amount of data that you have for your target system only. The other architecture consists of an LSTM coupled together with an autoencoder. In this particular case, what you try to relearn with the new data is only the LSTM part, meaning that you're trying to relearn the dynamics of the system, the temporal information that is relevant. And there's a third approach that is actually relatively simple. It's called seasonality adjustment. Basically, you apply some advanced pre-processing techniques. You try to remove the trend, the seasonality, and with the obtained variables, you basically go and train a multi-layer perceptor, which is a very popular standard neural network architecture. We tried a fourth approach, and we were not successful in obtaining reasonable results with this one. It's called domain adversarial neural network for regression. And this is a complex approach where you try to train 2 neural networks. And one of them, you train them for generating data, the other one for learning from that data. But we could not stabilize that learning process, at least for the real data that we were using. So the flow for the methods and the benchmarking metrics can be highlighted in this figure. See. So we have a source building and we have a target building. We considered what happens when we have around 20% of the original data, 40%, 60 or 80% of all the data that we have. We had data from 2 seasons, for the fall and for the summer, which are one next to the other, and for each one we have around 10,000 observations, ballpark. We train a base model, meaning that we use all the data, and we want to compare what happens when we apply transfer learning techniques with limited data, and what happens when we compare the performance that we obtain with respect to that base model. And basically what we want to quantify in this case is the positive transfer, which means that we improve the accuracy over the base model. The measure of performance that I forgot to mention that we use is based on this formula, where mean absolute error of the base domain, it means one building. We compare that with the mean absolute error of the target domain, which is basically a different building. And for the results, as I just previously mentioned, we investigate what happens when the data availability changes from nothing to 20 to 40, 60, and 80%. And we try to analyze which transfer learning method is better, and we also try to analyze what is the difference between transferring information from similar systems or what happens when you try to transfer information from different buildings. And I'm going to start discussing a little bit of the results. In terms of positive improvement with respect to the baseline, we found that the simple method, the seasonality adjustment, worked well with respect to the others. This basically means that your transfer learning is very positive for this technique. However, when you look at the base performance in terms of prediction capability of this technique, it's not the best. The best prediction capability that you can see here is going to be for the LSTM dense and LSTM autoencoder. And of those two, basically, they are much more stable than the seasonality adjustment. So an initial conclusion is that, okay, out of these techniques, seasonality adjustment seems to be better in terms of transferability, but it's not the best in terms of prediction performance. The most stable approach that we found was LSTM plus dense fine-tuning, meaning that we fine-tune everything. The thing is that the performance improvements in terms of transfer learning are less impressive, but this method showed a much stable result. When you look at this figure on the left, in green you show the positive transfer, meaning that you achieve something by applying transfer learning technique. When it's in blue, it means that there's negative transfer, meaning transfer learning did not help you significantly to achieve a better performance compared to the base model that you train. Then, when analyzing cross-season, using cross-season information in the same building, we observed some improvement in terms of positive transfer. For the three different approaches that we compared, again, seasonality adjustment achieved the best performance. And in the others two, you achieved some degree of improvement. When analyzing cross-building, same season transfer, meaning I use data from one of the buildings in the summer to try to fine-tune the model with limited data from the other building also in the summer, right? And under those conditions, we did not see such an advantage. This slide is just to highlight why energy prediction is relevant in the context of buildings, because by using the models that we trained, we analyzed test data that was not used, and we were able to detect some anomalous behaviors in some cases, which building operator managers, they appreciate if you have a model that tells you something strange is going on, that they cannot straightforwardly identify from just looking at the data. So we were able to identify some anomalies in the data by using these models. So these are some of the conclusions. Just to summarize, we conducted an experimental study on the applicability of transfer learning methods for building energy system energy predictions when using real-world data and internal HVAC measurements. We use different approaches and different combinations of target and sort domains to compare cross-season transferability against cross-building transferability. We hope that this type of research contributes to better energy efficiency, anomaly detection, and control of buildings. But our main conclusion is that we did not find a lot of benefit in some of these transfer learning techniques. Maybe this is due to the fact that most studies that you find in the literature work with simulated data, which is created to represent that problem. When you use real data from buildings, operational data that include measurements, these transfer learning techniques do not seem to be extremely relevant. And although this seems that a negative result that tracks this kind of techniques, what this indicates is that we need more research where we have real data that can be used to conduct experiments. Because with simulated data, you cannot really tell if these approaches are going to work. With that, these are the references included, and thank you for listening. If you want to contact, you can contact me or the first author of the paper. So questions are welcome. Yeah, let me.
Thank you for your presentation, and I have one question about the model design. Because you transfer from seasonally, but the summer and winter will use more energy than spring and autumn. So have you ever tried some special design for your model to address this kind of problem?
So in particular, yes. One of the facts that motivate this work is that you have limited data. Why do you have limited data in some cases? Because data processing and data management is extremely time consuming. So of all the data that we have from different years, we curated 2 seasons which in terms of energy consumption are the most relevant for the university, which is summer and winter, because temperatures vary significantly in those months in Nashville. This is given the weather conditions in Nashville. Temperature conditions and weather conditions in winter and spring, they are a bit more stable than compared to the summer and the fall. That's why we also wanted to have 2 continuous seasons. So summer is probably the month where most energy is consumed. That's why we included it here. But in the future, we also want to explore different seasons and different months of energy consumption.
Okay, thank you for your comments. And another question about the data size. Could you please show us the data size in source domain and the target domain? You use how many data in the source domain?
To answer that question, I think you have to go to the paper. I don't remember if I included the number of observations in the slides. Yeah, but it was around 10,000 observations. It was sampled every 5 minutes for each building. So it's 5-minute data for, over a range of around three months.
Okay,
so
thank you.
You can do
Thank you very much.
calculations. Okay.
If it's not the case, we thanks to Marco for the presentation, and we go to the last
Thank you.
one. Please come.
Thank you very much.
What is your name?
Chen.
Okay, then I want to introduce to Li Chen-Yi, who is going to speak about the system identification for battery stage prediction and lifespan estimation.
Thank you. Hello, everyone. This is Chen-Yi from the University of Manchester. And my topic today is system identification for battery state prediction and lifespan estimation. Is this?
You have to use the computer because that doesn't work with PDF.
Okay. First, I'd like to introduce the research background. Our research is mainly conducted on lithium batteries. And lithium batteries are extensively utilized across various sectors, such as portable electronic devices and renewable energy storage systems. And the following figure shows some research, some application aspects of the lithium batteries. And for the application of lithium batteries, it is important to monitor the battery state. For example, like the battery temperature and voltage during the charging and discharging duration, and also for the battery state of charge as mentioned and state of health as mentioned. And what's more, the modeling for the battery state is the first step of the model-based fault detection, because sometimes for fault detection we need to have an accurate model for the battery, and we can compare the measured output and with the battery and with the model output, and so we can identify some kinds of faults. And so, and this is our method. Our method is system identification method. Basically, system identification method is widely used in signal processing and dynamic systems. Traditionally, in system identification methods, the system dynamic characteristics is assumed to correspond to a specific model, such as the autoregressive exogenous model. The model assumes that the current system output depends not only on the input, but also on the previous output. Sometimes in some machine learning research or deep learning research, we focus on the relationship between the input and output. But in real systems, we always could get the real system output. So why not we use the real output as the model input? And so the ARX model structure is shown below, where YT is the model output and the UT is the model input. And this is a very simple linear combination. A1 to AN and B1 to BM is the coefficients corresponding to the input and output elements. And for the basic steps of system identification include giving the system a specific input and observing the system output, and then using the least squares method and other methods, we can fit the parameters of the model, and we can reveal the system dynamic characteristics. And in our study, we use the data-driven system identification method, which directly use known input and output data sets to fit the model. Because some system identification research, we use specially designed input to excite some frequencies we want. But for our research, we use data-driven, and the input and output is already known. So we can just use it to fit the model. And the model obtained in this way, we can process unseen input data and predict the system output. Sorry. Okay, thank you. And sometimes for some complex systems, if the linear combination cannot meet our requirement, we can also use nonlinear ARX model. It's also the system output depends on the previous output and input, but they are not linearly combined. We have a function f, and function f is formulated using the wavelet network. In this paper, we use the wavelet network, and of course, we can use other nonlinear functions to build the connection. And and for the model order selection, because we need to decide how many previous steps we want to include in the model, and the model training is achieved by nonlinear least squares method. And in the specific application of battery state monitoring, and the first one is battery temperature and voltage prediction. The model output is, of course, the temperature and voltage, and the model input is current, charge quantity, and ambient temperature. And for the state of charge estimation, the model input is current and voltage. And for the battery state of health estimation, the model input, there's no model input. It is autoregressive model only. Because actually for state of health estimation, it is cycle level. We only need to record the state of health during a whole cycle, but we don't need to record for example, the current or voltage in that cycle. We only need to record the state of health. So the current, the voltage is not considered as the input. It's an autoregressive model only. And unlike the state of charge estimation, for the state of health estimation, we consider one battery cycle as a time step. At the ARX model, as we can see, it is a time series model. So one battery cycle is considered as a time step. And this is a data set used in our research. It's open data set. And this is the results for temperature and voltage estimation. And we can see different color lines represent different temperatures and charging rate, like 1C, 2C is different charging rate. And we can see the prediction ahead time is set as 180 seconds in this figure. And we can see the temperature and voltage prediction give good results, I think. And for the other steps, for other times of prediction ahead time, for example, in the previous figure, it's 180 seconds ahead prediction. And for this figure, we can see that the lines with an increasing trend is our model result. And the dashed line is the result for an existing another method. It's you can see it's TSP ME models. Yeah, and we can see that the ARX model error increases when the prediction ahead time becomes longer. Because for the ARX model, the the prediction depends on the previous output. But the previous output, actually, it is predicted. So the error will accumulate in the ARX prediction process. So it has an increasing trend. And so, but for the TSPME method, it is not a time series method. So it gives a constant RMSE. It's not time series. It gives a constant prediction RMSE. So we can see our method about the 600 ahead prediction. Our method is the RMSE is similar with the existing method. And this is the results for state of charge estimation. We can see the left figure is state of charge estimation for a specific cycle of 3 different batteries. And we can see this is a prediction for a particular cycle. But actually, a battery has many cycles. So we conduct the state of charge estimation for every cycle of the battery. And we can see the results is shown in the right figure. From the left, it is 100% battery state of health. It means that it's a new battery. And we conduct state of charge estimation. And at the right, it is end of life. And in this paper, the end of life is defined as 80% of the initial capacity. And so from the new battery end to the end of life, our state of charge estimation have a mean relative error. Most of the mean relative error is lower than 6%. And this is the result for state of health estimation. As we discussed, the state of health is autoregressive model only, without input. And we use different sizes of training data set. For example, in the left figure, it's 10%, 15%, 20% respectively. And we can see that the model gave good results. And also we test the other size of training data set from the right figure from 3%, around 3% to 40% for different sizes of training data set. Although there are some research, they can give capacity estimation from very few initial cycles of the battery life. But sometimes they use measurements during the cycle, but not only the state of health only. So we can see in the right figure, when the training data set size increases, the MRE get fluctuation, and when it is beyond 27%, and the MRE becomes lower and stable, and that's interesting finding. But for the previous part, for the training set before 27%, there is fluctuation, and we think that that's because of the disturbances in the data set. Because we can see for around 7%, the model already have a very low RMSE, already have good results. But when the training set is bigger, the results get fluctuation. So that might become because some disturbances in the data set. This is a brief summary. We propose the system identification method, and for battery temperature and voltage prediction, and state of health, state of charge estimation. And this is the reference list, including our data set in the research. Thank you very much.
Thank you for your presentation. Questions?
Thank you for the nice presentation.
Thank you.
So, of course, battery dynamics is nonlinear and so on. So I understand why you use a nonlinear model for that.
Yeah.
But the hypothesis about the availability of the state of health measurements is quite stronger, not?
Sorry.
Because the measurement of a state of health, you suppose is available, but normally it's quite difficult to obtain that measurement.
Yes, but for the training data set, we can see it's only maybe 7% or 10% of the total life. So for this battery, it is cycled from the new battery to 80% of the battery initial capacity. So if it's 10% of training data set, the battery might decrease of 2% capacity, total capacity. So that's a few cycles, so we can get the model. Only a few cycles. So, and after that, we can use the model to predict.
Okay, I understand. And you expect that your model can predict more than 80% of degradation?
I think that will be in the future research.
Okay.
Thank you. Thank you very much.
More questions? I have a quick question for you. Oh,
Hi, thanks for the presentation. Can you go back to slide 13, that one?
13.
So on the right-hand side,
Yeah.
Can you just explain to me what the different coloured lines are on the legend? I don't understand the 100 steps, 200 steps.
Yeah, different colors represents different prediction ahead steps. For example, ARX model, we can, it's the K-step prediction technique of ARX model. We use, basically we use the output, and we do not give the current output, and we just use the output and predict again and again to just like a loop. And for different steps, you can consider it as different loop steps for prediction.
Okay, thank you. That's clear.
Yeah, one last one. Yeah, it was exactly about that figure that I wanted to ask you about. So very briefly, the behavior that I observed when you, in that right-hand figure, it's a little strange, because sometimes seems like adding more data makes the performance worse.
Yes.
How can you explain that sort of unstable behavior?
Yeah, because because sometimes I think it is the problem of the data set, because we can see in the left figure, in the initial data set, there is a big step of the stable health. There's a big step, and for some other batteries, there's also some, I think it's some measurement error, because there's a very big step in the measurement. So if we get this into the data set, it will influence the model performance, I think.
Any other question? No? Okay. Thank you very much for attending this session. Hope we can continue productive discussions afterwards.
Thank you very much, everybody, for the assistance of the audience.
Yeah. Oh.
Yeah.
Thank you. Sure.
Maintenance. I'm Johnny Lam, and it's my honor to co-chair this section with Professor Alessandro Passavoli. And we have all the 5 speakers here, so we are ready to go. And let's move to the first paper, an approach to secret sharing-based secure remote monitoring. And the presenter is Professor Zhang.
Yeah, thank you very much. So good afternoon, ladies and gentlemen. So welcome to my talk. So here, my name is Zhang. I'm from the University of Kaiserslautern-Landau. This is a cooperation between the University of Kaiserslautern-Landau and the Donghua University in China. So here the main purpose is that we want to explore how and whether we can use the security sharing for the remote monitoring purpose. So at first, remote monitoring, so where we need the remote monitoring, there are some typical scenarios that we use remote monitoring. For instance, in big enterprises, so they build up remote monitoring center to monitor different plants so that they can improve the efficiency of the maintenance. And they want also to compare the performance between different plants. And second typical scenario is that the equipment providers namely also built such remote monitoring center to provide the so-called life cycle service to the equipment that they sell to the customers. So one thing is in common. So the main purpose of the remote monitoring is namely to improve the efficiency of the maintenance services. On the other side, so the signals in remote monitoring centers are often transmitted over the network. So here, it is more flexible, but on the other side, the signals transmitted over the network may get attacked. So it may happen that some attackers will eavesdrop the signals, so namely to try to get confidential information. And if the remote monitoring center is hosted on some third-party cloud platforms, then it may happen that the cloud providers are honest but curious. That means they will carry out the operations correctly, but they're curious, so what is inside the data. So now the question is how to protect business secret. For instance, so how much is now produced, and the working conditions of the machines, so how to protect this kind of information so that they are not accessed by the people who doesn't have the access right. So here we have indeed different strategies to handle that. So one way is namely to do the encryption. So namely, people tries to encrypt the signals sent over the network. So in this way, we can protect the information in the signals transmitted over the network. And if the people want to protect more, so not only the signals transmitted over the network, but also the parameters of the system. So for instance, the system model and system monitoring system parameters, so they can also use the so-called homomorphic encryption. So it's a special encryption approach which can both protect the signals and the parameters. So with the encryption approach, so one of the problems is that usually it handles big numbers with many bits. The question is there some other possibilities to protect the information? So in this paper, so we try to apply the secret sharing. It is another technique provided by the computer science, and to check whether we can use it for our purposes of remote monitoring and whether the calculation can be carried out in real time. So that is our main purpose. So before we do that, at first, several words about the secret sharing. So the secret sharing was proposed before a long time, so by the Shamir, the very first work, and then it was continuously developed. So the basic idea of the secret sharing is indeed quite simple. So namely, if I want to transmit a data over the network and I don't want other people to read the information, I can divide the data into several shares and transmit them through different channels. So only the receiver which has received a certain percent of the shares, so they can reconstruct the original data. So here, this secret sharing technique, they have been already widely applied indeed in the everyday life. So for instance, for the parties communications over public channels. It is popular in the e-voting systems. It is used and also in the image and audio records. So people use it to protect sensitive information contained in the medium. In the control field, so the group of Darup and co-workers has applied it to build up some linear feedback controller to protect the information. And then they have extended it to the polynomial controllers before 2 years. So our purpose is namely to check the performance for the remote monitoring. So now, at first, about the basic idea of this technique, so how it works. So at first, we look at, so we assume that we have the number p here, so it is a positive integer. So usually it is some big integers, but not so big as usually we use in the encryption. And we define a set. So the set ZP, so capital letter Z P, so it means that so all the integers between 0 and p minus 1, so it is this set. So now if we have an arbitrary integer from this set, so we can divide it into 2 shares. So one share is randomly generated. So we randomly generate the t here. So t belongs to this set between 0 and p minus 1. And then we calculate the other share. So the A is calculated based on the original data z and based on the randomly generated t here. So it is just z plus t and then mode by p. So surely, because of the mode operation, it belongs also to this set. So it is an integer between 0 and p minus 1. And now, so these 2 shares will be sent over the network separately in different channels. And the receiver on the other side of the network, so he has to get both pieces, so both T and A. So if the receiver has both pieces, it is possible for him to reconstruct the original data Z. And namely, it is very simple. So it is just Z equals to the A, the share A, minus the share T, and the mode by P here. And now the question is, so how about, so here we have only positive integers, so in a certain range. So how about if we have an arbitrary integer, could be also negative values. So in control system, very often we have also some negative values. So how to do that? And so the people handles it in a quite simple way. So let me now assume that we have a number eta, and this eta is an arbitrary, is an arbitrary integer here. And then in the first step, we do a small operation. So we take the eta mode p here. So this z, we transform it again into the set between 0 and p minus 1. And then we do it in a general way. So we split the z into 2 shares, a randomly generated t and the calculated a here. And we send both pieces over the network. And then based on the a and p received by the receiver, so here we can reconstruct the z at first and after that, but recall that, so this z, it is just a number between 0 and p minus 1, but our original data is indeed some integer number, could also be negative. So how to get it is also quite simple. Namely, we apply the so-called recover function. So by this recover function, we can get the original data. And it can be proven that, so here we can get exactly the original data, as long as one condition must be kept. So namely, when we select the value of the p here, we need to take care that the p is bigger than 2 times the absolute value of the eta here plus 1. So that means there's some requirement. P should be big enough, in other words. So now, let's consider our problem of remote monitoring. So here we have our plant, and assume that we have some local controllers, we have sensors, actuators, so they are indeed together. So the people are interested in that. So the sensor signals, so namely the Y here, and the control input signals, they will be transmitted over the network to some remote monitoring center, so which is on the other side of the network. So we have the signal Y transmitted, and we have the control input signal transmitted. And on the other side of the network, we build load our residual generators, we evaluate our residual signals. So here we consider a very simple system. Namely, we have a linear time invariant system, and we have the standard description here, U is control input, Y is measured output, sensor output. So these some unknown disturbance, and F is the fault to be detected. Now we apply the circuit sharing. So in the first step, to just explore the basic idea, we make some simplifications. We assume that the system matrices are integers, and after 5 minutes, we will extend it to the case that if we have real numbered system matrices, we assume also that the initial state it is some integer. And now what the people do is indeed quite simple. So the sensor output here, so that is the Y here, we want to transmit it, so we split it into 2 parts. So namely, we will generate a random vector, Sk here, and then we calculate the other share, so C, by this formula we have seen just before, so we'll take it. And then the control input signal will also be split into 2 parts. So one is randomly generated T here, and the other part is namely the W calculated based on the original data U and the T here. And then we will send different shares through different channels. So in the one channel, so the randomly generated S and T will be sent. So this red part, a piece of information will be sent to the first cloud. And we send the other share of each signal to the other cloud. So namely the C signals, these blue signals, and the W signals to another cloud, so cloud 2 here. And after that, so each cloud, we have implemented a residual generator. So you see that in each cloud, they have only part of the signal information. So no cloud have the total information. They have only part of the information. And indeed, the residual generator in each cloud is constructed rather easily. So namely, if you look at it, it looks just like the standard residual generator that we are very familiar in model-based fault diagnosis here. So we have some observers, and we generate the residuals here. The only difference is that here in this cloud, so we have only part of the information of sensor output, and we have also only part of the information of the control input. And similarly, we will also send the other part of information to the other cloud. So the cloud 2 here, the other cloud 2 here will have indeed, the formula looks similar, and the difference is that, so it has also only part of the information. So it has a blue part, so namely part of the output and a part of the control input. And so in this way, in both clouds, we have the so-called partial residual signal. So we have this R hat 1, R hat 2, and if you look at it, there are some very big numbers. You can get no information from that. And then, so these residual signals, these partial residual signals will be sent through the network to the residual fusion part. And in the residual fusion part, it carries out a very simple calculation. So namely, it just takes the difference between these 2 partial residual signals and use the recover function, if you remember. So we use the recover function here, and in this way we get the final residual signal, the R hat. And now you may wonder, so what is indeed in the R hat? And if we look at the dynamics of the R hat, we'll find out that, so here we can do some simple derivations, and finally we have the residual dynamics of R hat. If you look at it, it looks just like the standard observer-based residual generator. So it is, that means no information is indeed lost. But on the other side, so even though we don't lose any information on the other side, you see that in the cloud 1, we have part of the signal information. In the cloud 2, it has also only part of the signal information. So we didn't draw it here. In the cloud 3 here, it has also only a part of the information. And if somebody gets only access to this cloud, he can do nothing with the signals here. So that means the signal are kept confidential, and we achieve our purpose of remote monitoring. Okay, so here that is, we see that, okay, we can get the same residual dynamics as in standard observer-based residual generator and without losing any information. But now the question, usually our system coefficient matrices, they are real valued numbers, so we don't always have integers, or in very seldom we have integer coefficient matrices. So how about non-integer coefficient matrices? So in that way, we need to do some quantization. So namely, we look at the signal range from minus alpha to alpha, and we quantize the signals here and equidistantly, so from minus alpha to alpha, and quantize it. And the step size is just a beta inverse. So you can imagine that the bigger beta is, and the finer is the quantization. But on the other side, we have then bigger numbers, bigger integer numbers. So what we need to take care if we do that is that, so now when we split the data, so here instead of the y, the output, so we need to multiply it not by the because of the quantization by the beta here. But otherwise, it's the same methodology. And then if we build up, so indeed that is the main efforts in deriving it. So when we build up the partial residual generator in each cloud, we need to take care about the beta factor, so the quantization factor. And if you check it, you will see that, okay, so here we really need some efforts here. So we need to multiply it at different places, so with different beta to get it working. So here it has cost us indeed the most efforts in developing this approach, but after we have got it, indeed it looks also quite simple, and we generate again the partial residual signals, the R1 and R2 here, and then we do the fusion of the residual signals, so we get the final residual signal R here. And the key here is namely two things. So the first one is namely we need to think about how to select the value of P here. So P will influence each step, so how to select P. So P should be big enough, but how big? And so we have given the formula in the paper. And second thing is that because of the quantization, there will be some quantization error. So the question is how to calculate the threshold. So now we need the threshold to make sure that we don't have false alarms in the fault-free case. Okay, 1 minute. So now we summarize it up. So we select the value of P and we split the sensor output signals, control input signals. We send the shares through different channels to separate clouds, and we generate partial residual signals, and then we combine the partial residuals, combine them together, we calculate thresholds, and we detect the faults. And just very quickly, the example, so I need 1 minute more. So here we use the 4-tongue system to do the example, so very famous benchmark system. And here, that is our observer gain designed in the Euro way, and so our control input signals, measured output signals. So I just want to show very quickly. So here, in the fault-free case, if you look at the signals here, so the blue line is namely one of the partial residual signals, so in the cloud 2. And so the red line here, it is namely the partial residual signal in the cloud 1. And the true state is namely, so the solid, so the black line here. And you see that the state estimates in neither clouds, in cloud 1, cloud 2, doesn't indicate much information about the true state. But if we fuse them together, so that is the magenta dash line here, and it has a quite good overlapping of the true state. So here we can get a very good state estimate, so after the initial transit. So here we have in the initial state, surely we have a little bit the estimation error. And then just one example of the faulty case. Assume that we have an actuator fault in the first pump, in the pump 1. And the fault has happened between the 300 and 550 seconds. And so that is the residue generated, the final residue signal plotted. And so the fault can be detected rather quickly in the 40 seconds here. And so about the other faults we have simulated, so it is stated in the paper. So now summarize, so here in this paper we have developed a secret sharing based remote monitoring approach, and basic idea, split the data transmitted over the network into multiple shares, and it can be extended to K shares, and advantage is that we increase the confidentiality of the signals transmitted, and we work with smaller numbers in comparison with encryption-based approaches, and each cloud has only the partial information. So thank you very much for your attention.
Okay, we have time for a quick question. Is there any question from the audience? Okay, I have a question. So in your paper, you have used 2 clouds. Is it possible to use more than 2 clouds?
Yes, it's possible. So indeed, here to illustrate the basic idea, we used to just split it into 2 shares, and indeed it can be also split it into multiple shares.
In that case, I guess you have a more complex coupling between the clouds, right?
We don't have much coupling between the clouds. Only we need to take care about synchronization and so on. But indeed, the clouds works rather separately.
Okay, thank you. Let's thank the speaker again.
I will introduce the second speaker. He's our chair. Sorry, I have problem to see. The paper is entitled Runtime Monitoring and Fault Detection for Neural Network. Okay, it's presented Dr. Orlando.
Okay, thank you. So I'm Jiang Lan from University of Glasgow. So this is a joint work with Dr. Shi Zhan, Ron Patton, and Xinjian Zhao. And for this paper, we although we have the neural network as a keyword in the title, but we are not really focusing on the neural network training. We focus on the monitoring and fault detection for a control system with a pre-trained, with a well-trained neural network. Okay, so this is the outline. And a bit of background. So nowadays, deep learning methods such as neural networks are becoming more and more popular for perception modeling and control of systems. So especially complex and nonlinear systems. And this diagram just is a simple graphical view of these kind of systems. So each of the plants can be modeled by neural network, and the controller can be neural network. The perception can also be neural network. And so, but we know neural networks generally don't have a formal performance guarantee in real-world deployment. And also, it has been proved that, or it has been shown extensively that the neural networks, especially the large-scale ones, are very vulnerable to input perturbations. So these perturbations sometimes can be very small noise, and also some adversarial attacks. So this motivates us to consider the safety assurance of neural network controlled systems. It's because now you have the neural network within the closed loop. So if there is error or fault within the neural network, it will propagate over the closed loop, and it becomes worse and worse. So there are a few relevant existing measures. The first category is formal measures. But these measures focus on verifying the safety of stand-alone neural network components. For example, the vision neural network. And in other words, these measures are working on the open loop settings. And the second category is reachability analysis. This measure is working for the closed loop, but because they are dealing with set operations, so they are in general computationally expensive, and it's not ideal for real-time implementation. And the most relevant piece of work is the runtime safety monitoring for neural network control systems using interval observer. So in our paper, we also use interval observer. But in the existing work, they can only achieve conservative intervals, and they do not consider any disturbance or noise in the system. But disturbance and noise are inevitably in the real world. So our paper proposed a new interval observer to overcome these drawbacks. Okay, so this is a bit of the problem setting. So we consider this kind of discrete time nonlinear systems, and here the X is the sixth state, U is the input, and it in our setting is a deep neural network. And I will give more details in the next slide. And Y is the measured output. And so for our observer design, we can only use the measured output and also the control signal. And GXT is the node system nonlinear function. Omega T and VT are the the disturbance and measurement noise. These two signals are unknown, but we assume that we have their bounds that are known in advance. And ABFC are the constant matrices. So here are more details about the controller. So it's a deep neural network, and it's the feed-forward network. It has an input layer and layer -1 hidden layers. And for each hidden layer, it has an activation function, phi. Phi is a red-loop activation function in our setting. And the red loop is the figure here shows what does a red loop activation looks like. So if the input to this activation function is less or equal to 0, then the output of the activation is always 0, as shown by the red line. And if the input is larger than 0, then the output is equal to the input. So the network also has a linear output layer. So this is a neural network. And the input to the neural network contains a node reference signal, RT, and parts of the measurement output, YTO. So our design goal is to design a robustly stable interval observer based only on the measurable signals UT and YT. And we want to estimate the real-time lower bound and upper bound of the system state. So a simple example is shown in this figure. So here the black line is the real system state, the real values. And we have the red line is the estimated upper bound, and the blue line is the estimated lower bound. So this is the observer. We expect the observer will generate the red line and the blue line. And the applications include runtime safety monitoring and also fault detection. Okay, so this is what does the proposed interval observer look like. Basically, the observer has two dynamics. So the first dynamics 2A generates the upper bound of the state, and the other dynamics 2B generates the lower bound of the state. And so what we need to design here are two things. So LRO is the gain matrix to be designed, and we also need to design the bounds, or we say generate the bounds for the neural network and the nonlinear function. And for this omega t and vt, these bounds are known, are the known bounds of the disturbance and noise. So the design goals, the design objectives are in twofold. So the first one is sound state bounds, which means if the initial system state, the real system state, is within the bound of the interval observer, the initial interval, then we want to make sure that the real-time system state xt is always within the interval generated by this observer. The second objective is we want to make sure the observer, the interval width, so it's the distance between the upper bound and the lower bound generated by the observer. We want to ensure this bound is robustly stable against the disturbance, noise, and the possible bounding errors of the neural network and the nonlinear functions. So let's first look at how we generate the bounds of the neural network controller. So the first measure is auxiliary network measure. So this measure has been used in the literature, and basically it separates. If we look at the weighting matrix of each hidden layer, each layer in the neural network, basically we separate the weighting matrix into a positive part and a negative part, and then we use these two parts in 3B and 3C to generate the lower bound F underline and the upper bound F bar. And we can see that actually these two parts are actually coupled with each other. And either in 3B we can see it also use the lower bound, and in 3C it also use the 3B you also use the upper bound. 3C you also use the lower bound. So they are coupled with each other. And we propagate the input bounds, which is the null reference signal, and also the lower bound of the partial measurement and the upper bound of the partial measurement. So all this measure is computationally cheap because it only involves algebra computation, but it propagates the concrete bounds. So it resulting it gets a very loose neural network interval, so which reduces the precision of the observer. So we propose a new method which uses an optimization method to get the bounds. The key idea is that we notice that actually each red rule neuron, although it's nonlinear, it can be equivalently represented by a set of linear constraints, linear conditions. And we only need to introduce an integer variable, which is sigma ij here. So sigma ij can take the value of 0 or 1. If it's 0, then the neuron is inactive. If it's 1, then the neuron is active. So by using this mixed integer encoding, we can formulate the computation of the bounds as this mixed integer linear problem. And we solve this problem using existing solver like Wurobi to get the bounds. Okay, so now I want to briefly talk about how to get the bounds of the nonlinear function. So we can look at this figure here. So firstly, the black line is the Luya signal, and here we use the example of gix equal to x squared, and we look at the interval, the input interval x between -10 and 20, and to get the upper bound and lower bound, we divided the interval into several sub-intervals, and then we use the sequence line or the tangent line to connect each of the two neighboring points, and then we use a linear combination here to get the upper bound and the lower bound, and these two bounds are for sure they are the upper bound and the lower bound of these of the Luya signal. And we can also refine the bound by using the prior knowledge of this nonlinear function. For example, in this figure, because the nonlinear function is x squared, so we know for sure it's okay. So it's less or equal to 0. So we can then constrain the lower bound to be a non-negative value, and then in the last step we consider because we only have the states interval, so we use the optimization problem to compute the final bounds for the nonlinear function. Okay, so the design of the GAN matrix ARO is formulated as this ARMI problem, and 6A, this constraint is used to ensure the soundness of the interval, and 6B is used to ensure the robustness of the bound width. I won't get into the details. So we use H infinity method to get this ARMI problem. Okay, so we can apply the interval generated by the observer for forced monitoring. So the idea is simple, because we already got the interval. Then if we are given a safe interval, then we can just compare the generated interval and the safe interval. If the generated interval is within the safe interval, then we know for sure the state is safe. If not, then actually the safety is undefined. Undefined means that the interval can be too loose, or the state is indeed unsafe. So, but we don't have the determinant conclusion. Okay, for safety errors is similar. What the difference is, now we use the predicted, one step ahead predicted interval, and we check the set inclusion. Okay, so fault detection, we consider actual fault. So this is an additive actual fault in the control signal. And also, we check whether the signal is within the generated neural network bound or not. If not, then we know there is a fault. And we also consider sensor fault. Because the neural network controller use partial output measurement. So if there is sensor fault, FS, in the output, then it may change the control signal. So again, we checked the output measurement and the generated interval. And we can also use the difference combination of these two to check whether there is actual fault and sensor fault. One point I want to highlight here is that actually the neural network may overobserve may hide some small sensor faults. And also the sensor faults and actuator faults may kind of cancel each other, so they hide each other. And we cannot see, if we only look at UT, we cannot see whether there is a fault or not. Okay, that's a simple application in the adaptive control problem. We have two vehicles, and we are controlling the ego vehicle by a neural network to follow the lead vehicle and also maintain a safe inner vehicle distance. Okay, so these two figures shows that we compare two measures, the optimization measure OP and the auxiliary neural network measure, and we can see that the OP measure generates a much tighter bounds for the neural network on the left-hand side, and also for the acceleration. But we should note that for the least acceleration of the lead vehicle, we actually, both intervals are actually saturated at the constant value. This is due to we only use the largest possible bounds for the lead vehicle acceleration, so we don't have more information. Okay, so these two figures shows that also the OP generates at least as good as possible the bounds as compared to the AM method. Okay, so for detecting actuator faults, we have a additive actuator fault, and this shows that the figure shows that sometimes the black dashed line will go beyond the two red lines, but it's always within the two blue lines, and which means the OP method can detect this actuator fault, but the AM method cannot. Okay, we also consider sensor faults. One sensor fault at the measurement of the lead vehicle position, and the top figure just shows that if we only look at the neural network bounds, we cannot detect the faults. But if we look at the measurement output interval, we actually can detect the faults. And another sensor fault in the velocity of the leading vehicle, and in this case, is similar. We can detect the faults by look at the measurement. Okay, so a big conclusion, I will skip this. And so one future work is that we need to, now we have detection of the fault. We need to design a measure to ensure the system can be safely operating. Okay, thank you.
Thank you very much for your nice presentation. Just very quick questions, if there are. Are there any questions? Just, I would like to know, what is the role of G in the system? At the beginning, there is this. What kind of signal do you think?
Which
G? Yeah,
GXT?
Yes.
Oh, this is the nonlinear function of the system.
This is what kind of?
It can be a nonlinear lattice, so like sine, cosine, etc. Nonlinear lattice. Is from the system itself.
Okay.
Not design.
Okay, thank you. Okay, thank you again.
Okay, so now let's move to the third presentation. So it's the paper, a shape-based monitoring method for variable trajectories of finishing mere processes and is presented by Yilin Wang.
Okay, thank you. Good afternoon, everyone. My name is Yilin Wang. I come from Tsinghua University. It's my great honor to be here to present my work, recent research, a shape-based monitoring method for variable trajectories of finishing mile processes. Okay, this is the outline. And firstly, let's start with the background. It's a framework of the hot strip mile. And the hot strip mile is a batch process in the steel industries. Within this process, the finish mile process is a crucial subspace in it. And it is important for the key performance indicators, that is KPIs. And there are several stands in the FMP, and each stand is very important. Considering that KPIs cannot be accessed online, it is needed to be efficiently monitored. The KPIs should be monitored. As for the data characteristics, there are two issues. First one is the uneven lengths. It means that due to the variation in the practical producing conditions or the variations of the raw materials, the sample length from different batches may be unequal. And for the second one, there may be multi-phase characteristics. That a chip has to go through distinct phases, including the threading speed, the acceleration, and steady operation, and the decelerations. So, for this kind of batch process, there was a number of related researches for the batch process with these characteristics. Firstly, as a widely used method, multivariate statistical process monitoring methods, such as the PLS, PCA, CCA, and their extensions, have been applied to the batch process monitoring. But they cannot deal with the multi-phase data, and the point-wise monitoring manner is also sensitive to the noises. So a number of studies have been proposed to monitor this type of batch process with these two characteristics. Firstly, that the batch alignment is always needed for the uneven data, such as using the indicators, substituting time to a suitable indicator variable, using the based on the prior knowledges or the DTW to realize the batch alignment, but it is sensitive to noise. And the next one as for the multi-phase characters, they always need a clustering method, and based on the extractor features, the multi-phase can be divided into distinct phases, but this type of method may sensitive to the phase segmentations. So a good idea, instead of using the point-to-point methods, monitoring a variable trajectory monitoring, that using the entire trajectory to as a sample to monitor the state of the process is more challenging, is more better, because they can avoid the two above mentioned two characteristics and use the entire trajectory. There are several metrics to measure the trajectories. The first one is the model of feature-based metrics. But for this type of methods, finding a suitable model of features is difficult for the batch process data. And for the second one, distance-based metrics may meet the curse of dimensionalities when the number of samples is very large. And so we adopt the third matrix, that is the shape-based matrix, such as the DTW and SBD. This can measure the shape differences between the characteristics. And compared with the DTW, SBD is more robust and invariant to the scaling and the shifting. So we will introduce our problem formulation, and first they introduce the SBD metric. Okay, firstly, we define a cross-correlation function that is the capital R. This can measure the correlation between two trajectories, x and y. And then we define a CC function that is related to R. And then we have the normalized form NCC, and based on the maximizing the Meiding NCC, we can obtain the SBD. That is the metric we used to measure the shape distance, the difference between two trajectories. And based on the SBD, we can also obtain the central trajectories. It's a representative trajectory of a cluster. Here, the cluster means a group of curves or trajectories with similar trends, shapes, and so on. So we based on the central trajectory and the SBD, we have the following basic idea that for an FMP trajectory dataset X, and each of them is a trajectory, it's curves that is with a dimension of Li. And according to for the FMP, there are some PPI, some characters such as the steel grade and the thickness of the slab. According to this, we can partition the dataset X into XC, and the C there are capital C clusters in the dataset X, and based on the SBD, we can obtain the central characteristics of each cluster, and then design the statistics between the samples and their corresponding central trajectories. And then we will introduce our method. Based on the SBD, we designed two statistics. First is the D statistic. It measures the shape similarity between a sample and the corresponding central saturates. And here X is the sample, and the mu C is a central trajectory. And the second one is the S statistics. It measures the phase alignment degree, which means how large offsets it needs to align a sample to a central trajectory. And this is its interval. And it should be noted that S statistic is generated along with the D statistic. That is the specific value S is obtained when the formula, that is the first formula, is maximized or minimized. Let's consider an example that in the left picture, when two curves or trajectories are aligned, that here at this time we can calculate the similarity or SBD between these two curves. Then we can get the D statistic, and at the right side, that when we calculated the D statistic, we can also obtain offset that is in the red circle in the picture. Here is the offset we can get, and that is S statistic. And as for the control limits, there are two methods for these two statistics. As for the D, we use the kernel dentist estimation, that is the KDE to select a control limit under a specific control confidence level. okay, in the picture is a red point, and as for the S, we will calculate the minimum and maximum values, and also add a relaxation factor delta in it to obtain the upper and the lower bounds. And next, we summarize our monitoring method in the form. And firstly, we will need four inputs. And the first is the training and testing sets, and the two parameters. That is the confidence level of and added term delta. And the first part is offline modeling, and we will get 3 control limits. And for the second part, we will for new coming sample, we will calculate 2 characteristics and compare them with the control limits. That's our monitoring method. And for the case studies, we use this set from an FMP stand, and the rolling speed is closely related to the KPIs. So we use this set, and it has an influence on when the previous stand has an anomaly. It will influence the subsequent stand, and the tension between 2 stands will decrease. And this is why we use the rolling speed. And this is our offline modeling results. And to evaluate the performance of method, we use DTW as a comparison. And the left one is our method, and the first sub figure is the blue line is training samples, and the red line is the central trajectories, and the second and the third is 2 statistics, and for the right figures, because when we calculate the DTW, there is no offsets can be calculated. So there is only one D static is printed here, and we will give the monitoring results for a testing set. There are 54 samples that include 51 normal samples and 3 abnormal ones. And the SBD method, that is our proposed method, can detect all the 3 abnormal samples, and the DTW cannot detect. And this picture, there are 3 characteristics that is detected by our method. And I'll give the form to present our method is outperformed that DTW based. And this is our monitoring results. We can see that the S statistic has all exceeded the control limits, which implies that the S static is very important. And as for the DTW method, they cannot exceed the control limit. So our proposed method is better for the trajectory monitoring. And we will give the conclusion. And SBD based, this is our conclusion that can handle the difficulties in the point-to-point monitoring method for this type of FMP data. And in the future, we want to extend our method to the multivariate variable trajectories. And this is our founding information, and this is our authorship. Thanks for your attention. Thank you.
I think we have time for a few questions. Are there any questions?
Thank you.
No questions? Right, let's.
Short question. So on the page 13, you have written 3 samples. So each sample, do you mean a sample trajectory, or do you mean really at one time point. So here, no? So
a trajectory is a sample.
One sample, right?
Yeah.
Okay, let's change the speaker again.
Okay, we change the chair. So the next speaker is Dr. Sadfari. Okay. The paper is synthetic generation of streamed and snapshot data for predictive maintenance. If you want to use the microphone,
Yes, please.
just this one.
I prefer microphone. Hello, my name is Arzu. I will present our work, synthetic generation of streamed and snapshot data for predictive maintenance. And I'm from Linköping University. I will start the motivation of the work. So in data-driven prognostics and predictive maintenance, the data contains information about the performance of the battery or the component during the lifetime. The goal is to generate models, build models that learn survival functions. The survival functions helps us to understand and estimate the failure time of the component. And it's very important from industrial perspective because predicting the failure time causes us to reduce the costs, and it's very good to be able to predict on time. But this data set, this has some challenges. This kind of data set has some challenges. Usually the number of failures are limited, so the data set is very unbalanced. The health indicator, or there's no measurement of the health in the data sets, and the number of available data sets are very limited. To address this problem, we generated a dataset that captures essential characteristics of the degradation mechanism. This work is a collaborative work with Scania. And for making this dataset, we inspired from a real-world dataset from Scania. For having this dataset, there are some requirements need to be fulfilled. We need to run the component up to its failure time to have a run-to-failure dataset. We would like to have a health indicator available, but this health indicator is not available for prognostic systems usually. We would like to have aggregated data with a lower frequency to have an overview of the usage of the data, and stream data with high frequency that is a detailed performance and usage of the data. And the dataset needs to reflect the variations in the manufacturing quality, usage profiles, and ambient conditions. Having this kind of dataset has many advantages, like it can be used as a benchmark for evaluating and comparing different survival prediction methods. Knowing in this dataset we know the grand truths that will help a lot, and it enables us to do more controlled investigations because the dataset is very flexible. Here you see a simulation setup from the dataset, from the data generation. Here we have some input datasets. They are randomized to represent different characteristics of the real-world scenarios. Then they are fed to a simulation model, the pre-implemented simulation model, and the model simulates the performance and the degradation mechanism of the battery. And here we have some outputs from the simulation model. So it's a high-frequency stream data, and from
using these data, we can extract some aggregated data. And in this work, we used battery data as a case study. Many randomizations are done to generate these data sets to represent the real characteristics of the real-world scenarios. But you can find the methodology in the paper, but here I will talk only about one of them, which is usage profile. The battery's lifetime is very dependent on the usage of the data set, the usage of the battery along the time. We defined 3 different usage profiles: intense usage profile with a deep discharge, like long haulage vehicles, friendly usage which the battery doesn't experience the deep discharges, so it's charged more frequently, and in between usage. And in real world, it's very common to the data sets that they change the type after some point in their lifetime. It can happen due to the change in the owner or the usage profile. Here, for this, the component changed the type, and the failure time is very highly dependent on the new usage profile. And it can happen at any time point of the lifetime in data set and in real world. In industry, it's very expensive to store the data as stream data because it's not efficient. It's very expensive for storing and for transferring this data. So one of the most common solutions for this problem is to generate histograms from the data. So for example, from this data, the histograms are generated, and they are very good summarize the usage of the data. And these histograms are very efficient to save. We thought that in this data set we have a health indicator and usage profile available, but they are not usable, they are not accessible for prognostics data because they are not accessible in real-world scenarios. But they need to be estimated by using usage operational variables. For example, in battery case, voltage, current, state of charge, and so on. So we can take a snapshot, make a histogram at this time point from the data set and use that for predicting failure time. But only having one snapshot here doesn't cover the type change here. So by just feeding this to the model, it would be very difficult for the model to capture this type change in between. So for that, the multiple snapshots are taken from the model. Usually in the real-world scenarios, the histograms are made in workshop visits. And here you see that, multiple snapshots are taken from during the lifetime, and it can be helpful for the model to capture these type changes. So here we have more histogram data at different time points. I will give a summary of data set. We simulated 5,000 batteries. We generated stream data with each 10 seconds and snapshot data each 10 hours. So for example, battery like with the 6,000 hours lifetime contains 600 snapshot data, and each snapshot contains 11 numerical data, and 5 histograms. And each histogram contains 100 bins in it. The histograms are state of charge, current, voltage, ambient temperature, cell temperature. So the most things that affect the battery life. But it was mentioning that here our goal is not to generate a perfect simulation of a battery. We want to generate a data set that is sufficiently complex for the prognostic algorithms. So in the following slides, we will evaluate our data set for different prediction methods. To see how usage profile affects battery life, we use the Kaplan-Meier. The Kaplan-Meier is a non-parametric maximum likelihood estimator that estimates survival function. Here, for different types, we calculated or we estimated survival function. As you can see, the expected failure time is highly dependent on the usage type. So for each type, the expected failure time is different. Also, the Kaplan-Meier is not able to estimate the failure time accurately. For example, for friendly usage, it estimates it will fail from 5,000 to 14,000, which is not accurate. And here we can see that the usage profile is not enough for failure time prediction, and usage profile is not available in real data sets. Then we used Cox proportional hazard, a parametric survival function estimator, and energy-based model, which is a neural network-based prediction model. And we saw that, as you see from the table, we saw that the integrated Breyer score and C-index are very very different. So here we see, when we use energy-based, we see improvement, and for C-index also, which is not very clear from this plot also. In this plot, two individuals from a test set is illustrated. This dashed line is the failure time. The solid line is energy-based, the survival function predicted by energy-based, and this one is for Cox proportional hazard. So the steeper survival function is the better, is more accurate, and perfectly we want a step function here. But as you can see here, if we compare results from Cox proportional hazard and energy-based, we see a great improvement. So we can say that the data set is sufficiently complex for neural network-based models also. The conclusion, we started from prognostic data, and we saw that we generated prognostic data that is the standard statistical models can improve it significantly, like Cox proportional hazard. If we compare Cox proportional hazard with neural network-based, we see that the data is sufficiently complex for neural network-based models. How you can use the data set? The data set and the simulation model and the prediction files are available in my Git page. You can use this model, this setup, to generate your own data set if it's required, or you can customize the simulation model, or you can take the data set and do prognostic like analysis or data-driven models development. You can use it for remaining useful life or survival function predictions. You can define censorings, and the data set is very flexible for censorings, for the number of components, and so on. And you can use single snapshot or sequential data. Thank you. Any questions?
Yes, thank you for the presentation. Probably okay.
Thank you for the presentation. When listening, I was wondering why you were using histogram. You said this is for saving memory space or to store the data, but in some sense you lose the time history of the, for example, the evolution of the state of charge. And this time history is important for the degradation of the battery, because I think it's battery underneath here. So isn't it a problem to lose this time history when you make your prediction?
That is kind of problem, but here we can, by using the histograms, we summarize this data set. We just summarize it, and this is one of the most common ways of storing the data in the industry. So in the real industry data sets, they don't usually save this file. They save this as a usage profile because it's a summary. It's very easier to save it. It's very easier to transform it, and it's like very efficient. You lose some data, but the thing we can do is here. You can take snapshots from different lifetime of the battery, so you kind of lose that data, but you know that this usage that is done during this time is for like this time interval. So like if you take enough snapshots, you don't lose data, but you store it in a very efficient way.
Okay, but we can discuss this. Okay, thank you.
Thanks for the talk. I have a question about, do your results apply to general batteries or a particular type of battery?
It's lithium-ion battery we used here, but that is our case study. Yeah, we used a lithium-ion battery.
Okay, so in your data set, you have a different type of
it has only a lithium-ion battery. Yeah,
thank you.
We use it.
Okay. So we thanks again. The last speaker is Dr. Jing Yang. EMB is a selective preventive maintenance in improved availability for serious parallel systems.
Hello everyone, my name is Liao Jing. I'm come from School of Automation, Central South University, Changsha, China, and other authors is Peng Tao, Xu Yansong, Chen Zhiwen, Gu Weihua. All research is on IPM-based selective preventive maintenance to improve availability for serious parallel systems. And I will talk about 5 parts: introduction, problem description, methodology, case study, conclusion, and future work. So first is introduction. In industry and military systems, reducing downtime is very important. For example, railway systems can only be maintained between missions. Picture 1 is a downtime for railway. So by doing maintenance during planned downtime, we can greatly improve system performance. Maintenance results are often limited. So we must choose the best set of maintenance activities. It is known as selective preventive maintenance. And about the lecture review, in 1998, the preventive maintenance method was first proposed by Rees et al. Then Cassidy et al. Summarized the problem as a no-linger problem. Next, Samrot et al. Introduced an anti-Canning optimization algorithm to minimize preventive maintenance cost. In 2006, Kahedi et al. Considered the duration and the rest time of tasks as reason factors. Then in 2019, Zhou et al. Developed a fuzzy multi-objective no-linger model based on reliability and cost. Recently, in 2021, Zhou et al. Considered system reliability, maintenance cost, and uncercle. In 2024, Rudak modeled the maintenance problem as a job scheduling problem. And about gaps and main contributions. In our study, a reliability allocation-based programming model is proposed. We named it IAPM. The aim is to meet the required reliability level. Component reliability is allocated based on weights. The final result is a predictive schedule. And we use real data from the traction conveyor system of electric locomotives. Next, we will talk about problem description. Picture 2 is a strategy of traction conveyor systems, which have 8 IGBT commands. The 4-quarter repeater field and the event are designed in a module fashion, which is a AC, DC, AC traction driver system. This structure of the traction conveyor system have some notable advantages. First, it avoids the complex troubleshooting process and no longer a need for frequent installation of single IGBT components. The actual module can be directly replaced when any IGBT component within the converter module fails. And maintenance downtime is either planned or unplanned. Planned downtime includes regular preventive maintenance scheduled by distance or time. And unplanned downtime happens when an electric locomotive unexpectedly shuts down due to failure. Picture 3 is an unplanned shutdown for a train. And picture 4 is a result. Passengers stranded by a delayed train. So unplanned downtime is a major contributor to train delays and can result in considerable economic loss. Picture 5 is a preventive maintenance for electrical locomotives. Preventive maintenance for electric locomotives is divided into 6 levels, from class 1 to class 6. And the high line maintenance includes all low line repairs. Probability of module replacements have 2 results. On the one hand, it can enhance reliability and safety, but on the one hand, it can increase maintenance cost. So, effective maintenance of conventional modules is complex due to high cost and more replacement, and is a complex decision-making process. Next, I will talk about the methodology. In all research, the life distribution can be described by the Weber distribution. The Weber distribution as shown in Formula 1. Then, the cumulative Formula distribution as Formula 2. And next is a function of reliability is Formula 3, which I is the current subsystem sequence number, and J is the current unit carriage. K is the current module sequence number in the covered unit carriage. Picture 6 is a reliability block of the tension converter systems. The reliability of rectifier and event units in the subsystem is treated as a parallel system. So our tension converter system is complex, with 2 subsystems working in parallel. And the reliability of the rectifier unit and the event unit can show Formula 4 and Formula 5. The reliability of the converter subsystem show Formula 6, and the reliability of the inter-tension converter system as show Formula 7. Reliability requirements are set based on the life importance of each part. Note the width for each part change with the mean time between failures, which is namely MTBF. So the reliability requirements allocated to each core module can see Formula 8, 9, and 10. Figure 7 is an example form of decision elements of reliability allocation. So the reliability needs for each converter module make sure the system meets the required reliability. In our research, we have 2 objectives. Objective 1 is minimize the number of module replacement. Objective 2 is minimize the gap between the reliability of converter modules and the required reliability. And the reliability acceleration, the best programming model as shown Formula 14. Is an algorithm. The process starts with new electric locomotives and goes up to class 6 maintenance. The IPM updates the replacement status of modules with the biggest reliability gap until system reliability meets the requirements during planned downtimes. And now I will talk about a case study. We use a data set from an electrical locomotives company over a year, which have different types data, some measures, and the covered distance. We fit in the lifetimes of the current modules with the Weber distribution. This is the basis for a reliability analysis and preventive maintenance simulation. And we have three key performance indicators. First is availability. Availability shows the fault and repair features. Second is origin replacement rate. Origin replacement rate shows the mean level of feature or replacement of system competence, which is the mean replacement probability of current modules. Third is photo passage. Third passage shows the impact of a center fault in the system. Picture 8 is the result for the Weber distribution of current models. From the result, it is shown that these current modules have a big difference in Weber lifetime distribution, which is influenced by installation position, function, and working conditions. And the reliability requirement of the train current system is 99.5%. And table 2 is a result of reliability allocation. And from the results, we can know that the shorter the MTBF of the current module, the lower is reliability requirement. Modules that easy to features have lower reliability requirements. And all research reliability allocation have some advantage. It blends the overall system reliability. It can reduce the model replacement rate, and it have a low maintenance costs. Also, we consider the working real environment and real usage conditions. Picture 9 is the result for predictive schedule. The event unit complete replacement before or during class 4 maintenance, and with 2 to 3 replacement before the system-wide update. The Richter factor and unit with a low replacement compared to the event unit. And the picture 10 is the reliability of transient current systems and selective preemptive maintenance. All research successfully maintains the reliability of transient current systems at 99.6% or about. Compared with the actually application, the available rate is increased by 24%. So a balance between reliability and maintenance cost can be achieved by optimize the maintenance stage. Now, I will talk about the conclusion and the future work. We research the problem of selective preventive decision making in systems with serious failure, and the objective is to ensure the system achieves the necessary reliability with minimal interruption and delay. All must minimize maintenance cost and minimize the reliability gap between components. The future work have two. One is assessing maintenance cost and loss from task interruption. Two is predicting of outer future. My English is not very good. For your attention, thank you.
Thanks for the talk. I have a question about your future work. You mentioned predictive failure, prediction of the failures. Do you need a model? I guess you need a model or a simulation, at least simulation environment to develop the measures for predicting component failure, right? Currently, in this current paper, you only have real-world data. And how are you going to use this real-world data for predicting component failure?
We fitting data with we fitting the data with the lifetimes of the countermeasures with the Weber distribution. And then we get MTBF is a range of 1 year data. And first we get a reliability requirements and choose a best set of maintenance to maintenance. Sorry, my English is not very good.
Okay, thank you. We can discuss afterwards.
Other questions?
Thank you for the presentation. Could you go back to the slide where you compute the reliability of the system with the parallel and the series system? No? Could you go back to the slide where you compute the reliability of the system? No, before. I think it's before.
This?
No, before. Again, before. No, the previous one. Yes, this one. Why do you say that the rectifier and the inverter units can be considered as parallel system? Because it seems that the rectifier and the inverter are in series, And then these two series systems are in parallel with the other series rectifier inverter.
Someone can help me. Can I speak in Chinese or someone help me translation?
They say that the system are in series and in parallel. Question is why?
Or we can discuss this after, later.
Can someone help me translation in Chinese? Yeah. 老师。对。对对对。是的，他们是先串联再并列的。Yeah, as show in picture is first serious and then parallel. As shown in picture is a result.
Okay, maybe we can discuss after. Thank you.
Sorry.
Thank you again.
Sorry.